Okay guys, start typing on the chat window. I don't see a single message. What happened? Am I audible? At least type okay. Good. For a while I got worried. None of you are sending any message. What happened? You are not like that. এত শান্ত ছেলে তো তোরা না। Okay, at 90 we start. Last I saw was 110. So at 90 we will start. We have 88 now. Another 2 we will start. বাকি 10-20 জনের হয়তো লাঞ্চ শেষ হয়নি. They will join, but we'll give them an opportunity. Okay, let's start off. 92. We'll start off. 93. This is a known question now to you. You can see the timer now. Within the timer, it will close. So 9 of you could not answer within 30 seconds, which is bad. Please have a look at the timer. Still 7 of you got wrong. We explained that big theta is also an existing terminology, and you are still answering only upper bounds. Anyway, so let's move on to the next question. Is the score 70? Good, at least all of you remember that 2 to the power n will be the fastest in terms of time. The n factorial was also there, but in this choice it was not there, which is okay. Next question. Quickly. Nice, theta n square. I don't know why theta n cube came. Probably a typo. I'll leave it at that. Next question. I had given additional 30 seconds because you need to think about it. So this is not 30 seconds, it's 1 minute. Shayon Rongshoot Gitika. Wrong sheet, okay. Now I see completely new names here. Sohan, Angad I saw, Aditya, good. I see good leaderboards. Shayon anyway is consistent. 53. Yes, login. 12, 18, 13. 18 answered this. See, multiply log n with anything, it will be lesser than that. So if you multiply log n with n, it will be less than n. So if it is less than n, how can it be greater than the first number, which is n? You are asked to do slowest to fastest. So this is slower. So I hope that makes it clear. Let's move on. Omega. Omega means lower. who will be at the top is what they are asking. What happened? 27 Fn less than CGN. No. The function needs to have omega below it, na? So who is omega? Gn is the omega. So function needs to have below means Gn has to be less. Omega means below, lower bound. So function has to have somebody below it. Niche diye jabe. Somebody has to be below it. So who will be below it? Gn. So Cgn has to be less than Fn. That is the answer. Why 27 got you wrong? And this has no significance. Fn grows slower than that of Gn. No significance at all. Slower, faster, doesn't matter at all. Come on. This is bad. This is still better. Leaderboard has not changed much. This is still better. Thank you. Let's move on. This is big theta. Let's see if you can answer this. We have not talked about it, but let's see if you can answer it. Still okay. Leader Angad has come into 1, 2, 3. Good. 63. Let me see how many of you get this correct. I've been telling this many a times. If you remember, you can answer. Orkodeep Devosri, new entries. Good. Good. At least we are able to replace the leaders. 34. What happened? Worst. Total worst. Worst values of n. Large values of n. Yes. Asymptotic notations I have been telling you. That we only calculate for large values of n. Right, small values of n, these formulas are not applicable at all. I've been telling you this, na? That is the reason. Chalo, next. I'll increase the seconds here. You have some more time. 54. "25 of you answered Fn equal to OGN. Then Gn is equal to OFN." No. Gn cannot be equal to OFN. Gn has to be equal to something else, because they are asking you to find the order of Fn. So you are saying the order of Fn is the order of Fn, right? So that way it is a contradictory thing on B. So that way that was not the right answer. 54%. Okay, let's see this. "61. I mean, it was very obvious, right? Gn equal to order of n cube. Then which will be faster? Who will dominate means who is faster? Who will be above? That way you can think about it. So n cube is above n square. We know that, right? From the charts also, I saw whatever I showed you, right? It's n cube is above n square. So I don't know why you should think Fn dominates Gn. How can Fn dominate Gn when it is n square, Gn is n cube? Right? Could be a typo, but 20 people typo, still I don't believe. So that's on this quiz. Not very good performance, but let's see what is the performance. I don't know where this went. It said it could not sync and then went somewhere. Let me end this. I have to refresh it. Let's see what has it captured. Still can't get there. Give me 30 seconds, guys. Let me see if I can pull it out. Okay, we were here, asymptotic notations. Where do I see this? Okay, I'll have to figure out from where I can pull out the results. I don't know also. Somewhere here the results will be there. Don't worry, I'll pull it out. I'll share it with you anyways. Because the entire all quiz results I'm going to share with all of you. So I don't remember the first, second, third in the last question. But let's see what comes out of this result. In another, which one? So some of you are typing something. 1 minute, let me see. Show the QR once more. Where will we get the PDF? You'll get the PDF in the this one, WhatsApp group. Why not B? I don't know which question, so forgive me for that. What else is there? Misclick, same, no back for us. Gaya ranking. Sir, the QR, try the code, use code Abhinav Raha 20% discount, log and misclick, can you explain? That's what I explained, right, Zeniki. If Fn equal to Gn, then Gn equal to omega OFN. You are asked to find out the big O of Fn. Then if big O of Fn becomes again big O of Fn. So option B says it is big O of Fn. You are not asked to find big O of Gn. Right, so that's why it is, what's happening? Why is this playing? I don't know why this is playing. Anyway, so let's move on. Yeah, I think this is not on a live mode. So let's move on to the next topic. We will come back, and I explained this earlier also, but we will complete search now. Search will be small in nature, and then we will get into our main unit 2, which is tags and queues. It would be interesting at that time also, but search is also interesting. I'll tell you why. Because a lot of times binary search becomes a hot topic in the question papers. So we will quickly finish linear search and we'll get into binary search, spend some time there. Let me change the the window capture. Yeah, so now you should be able to see the screen. So I have nothing much to say on linear search. You have been doing it from last 1 year. Definitely all of you would have taken an array like this and you would have searched a number like this in this array. That you can do, right? And that algorithm is here, right? So what we do, we'll run a loop, and if the element of the array is equal to the search element, we will return out, else we will increment. That's the common way to do it, right? So that's how we will do it. And if the array element is not found, this return will never happen. So if it comes out of the loop without returning, that means there is a problem, target is not found. So this is how it is structured, right? So this part I am not going into detail. What I am trying to give you is the best case, worst case and average case, right? And I would have preferred to write theta here rather than O, but then you can use any notation for that matter. It's not just theta. You can write, because if it is a known complexity, then every complexity is the same. Theta is the same as big O, big O is the same as omega. But I would have preferred to use theta, but again, all three are same, right? Because it is a known complexity class. We have proven that. Now here, what do you see is that best case is what? When I say best case of searching this, that means I have searched for 23, I got 23. Right, so if I search for 23 out of 7 pockets and I get for 23, then my best case becomes order of 1, right? Which we know, because it is always going to be found at a constant amount of time. Every time it will be found at the first index position. That will be my best case. It will always take a constant amount of time. It is not 1 just because you are finding it at the 1th index. It is because it is being found at a constant amount of time, which is independent of the number of inputs of the array. Right, irrespective of how many elements you have, you will always find it at a constant amount of time. That is why it is order of 1. Worst case, the worst case is that in this 7 pocket array, it is in the last element. So then you have to go 1, 2, 3, 4, 5, 6, 7, 8 or 7 iterations you have to do. So the worst case is going to be 7 in that sense, right? So you'll have to take 7 iterations to actually find this particular value. So that's why the worst case becomes big O of the n, because 7 is, you can't write 7, right? Because it can be variable. The number of elements can be variable. So you'll have to write it as big O of n. That is my worst case. What is my average case? Whenever it is an average case calculation, wherever you see average case calculation, you will have to imagine that the search finds every element in independent runs. When I say that, it means that let's say I have searched for 23, then what is the complexity? What is the time? Let's say I have searched for 35, what is the time? So every run is independent. Assume every run independent and search for that item, log the time. right? Log the time means first run will take 1 unit of time, second run will take second unit of time, or 35 search will take 2 units of time because you will be searching here, then you will be searching here. So you will take 2 times of search, 2 times of comparisons. Is ARR 0 equal to 35? No. Is ARR 1 equal to 35? Yes. How many searches did you do? 2. That is why this 2. That is why this 2. And then forth, you will do the rest of the searches, right? Each individual element, if you search, how much is the amount of time that you take, which is going to be looking like this. So if it looks like this, then imagine this is 28 by 7 if you add it up, and then that becomes equal to 4. Now if this is 4, then how can I correlate this 4 with my total number of elements, right? I have to always express my complexity as an order of n, right? That n has to be brought into the picture. But what do I have? I have 4. 4 has to have a correlation with this 7 elements, right? So 4 is my total complexity. I have to now say that, okay, 4 is approximately 7 by 2, right? So if I take 7 by 2 and I take a ceiling of that, then I get 3.5 ka ceiling, right? So then I will get 4. So what it means this, I took 7, which was n, which was my n. So I took n by 2 ceiling, and n by 2 ceiling came to me as 4, which is my average complexity. That's why I can say my average complexity is n by 2, right? So average complexity has to be n by 2, and if average complexity is n by 2, asymptotically it will be called as big O of n. So again, I have not called it as theta, I have not called it as omega. I can call it as any one asymptotic notation as long as it actually marries a well-known complexity class. We all now know that, right? Do not forget this. If it is aligning to any one complexity class, you can use any one of the complexity notations for that. And that's why I've used big O of that. And the space complexity for this, to store these many elements, I need n what? N words of memory, right? So I need n words of memory to store this. That is what I'm saying. So the space complexity of this will be Sn equal to big O of n, which is n words of memory I will need. So one word in one machine can be 4 bytes. One word in the another machine can be 8 bytes. So just like time, right? So one instruction can take 100 milliseconds in one machine, and one instruction can take 200 milliseconds in another machine. Similarly, one word can have different annotations. So instead of saying megabytes, bytes, like we don't say seconds, milliseconds for big O or asymptotic notations, similarly for space we will say in terms of the words, and those words will be converted as a big O notation. Again, the same way as whether it is dependent on whether it is dependent on the number of inputs or not dependent on the number of inputs. If it is dependent on the number of inputs, what kind of dependency? Whether it is a straight line like this dependency, whether it is a curved line like this dependency, the same conventional complexity classes will come into the picture. All you need to calculate is how many words. So that's what that means. So that is on the linear search. The typical questions that come is best case, average case, worst case calculation, and an algorithm. Algorithm I have already shown you. Now here, so here what we have binary search. Okay. Now for binary search, let us understand what is happening. Binary search is basically being done in 2 steps. One we call as divide, another we call as conquer. So divide and conquer means that I will be dividing the entire search array into 2 halves, and I will search in those 2 halves where it is, right? And accordingly I will neglect one half, I will move forward with the another half. So that is where the conquer phase will start. So divide phase will stay, I'll keep on dividing. Conquer phase will say I will neglect one half and I'll move on, I'll try to solve the problem, right? So that is what is conquer phase. So binary search, first thing you have to remember, this is a divide and conquer, right? So this is a divide and conquer binary search. Second thing that you have to remember is that it needs a sorted array. because I will be discarding elements on the right or left, I have to be absolutely sure my right side of the array does not have my search element. So I have to be absolutely sure. So if I just draw a line like this, and I say that I am going to search on the left or on the right, and if it is not on the left, I will discard the entire left. When can I discard the entire left? When this entire left is sorted, then only I can discard the entire left. So let's say I am searching for 39. If I divide it here and I know it is on my right side, then I will discard this entire side. Because this array is already sorted, I have the right, and I will be right to do so also. Right? So that's what binary search requires. So the array must be sorted. It is a divide and conquer algorithm. And if I show you the exact nature of preconditions here, this is what it is. Array must be sorted. Very important. Elements must be comparable. You should be able to compare 10 with 12. You cannot have 10 here and A here. You cannot compare 10 with A. They are two different data types. So elements must be comparable. Second point. Third point is it must allow random access. Random access means I should not be forced that I will go here, then here, then here. Just like linear search, right? I am forced to go like this. Linear search. I should not be forced to do that. I can do a random access. I can access this. Suddenly I can access this. Suddenly I can access this. Wherever I want, I can access. These are the 3 points you have to remember for binary search. Right? So what do? You will actually take two things. One, you will take a left pointer and a right pointer. So you will take a left pointer here and a right pointer here. And in that left and right pointer, let us say our left pointer is 0, our right pointer is 14. Right now whatever is on the screen. And we will also take a mid as calculated value between left and right pointer. So it will be left plus right divided by 2, which will try to bring up the mid value, which will be floor of 7.5 by 2. Right? So floor of 7.5 by 2 is 7. So you can take any, you can take floor or you can take ceiling, it does not matter, because at the end of the day, 1/2, which will be not exactly 1/2, because in an even entity, you can create halves, right? For let's say 8 pockets, you can create halves, like 8 divided by 2 is equal to 4. 4 on one side, 4 on another side. But for odd entities, you cannot create exact halves, right? So for odd entities 9 by 2, you cannot create exact halves. So 1/2 has to have 4, 1/2 has to have 5. Whether you take ceiling or floor, it will mean that the left half is 5 or left half is 4. That's all it will make the difference. So that's why I'm saying that ceiling or floor here does not make any difference to the halves that are being selected. Now once you are done with this, what you will do is, let's make a dry run table. We will say L, R and mid. And we will start calculating this. And we will build the algorithm as we go along the way. So L is 0. R is 14, mid is 7. What we do is, at the value of mid, we will compare the target we want to search. What are we searching for? Let me clear this off. What are we searching for? We are searching for the element 39. So as you can see, I am searching for the element 39. So if I am searching for the element 39, then this 39, sorry, whether I was just checking whether my camera is moving or not. I hope my camera is moving, guys. Please type OK. Okay, thank you. Okay, coming back. Now here, if I take this 7, what I will check is, I will check if at the mid value that I have got, if my target is greater than the mid value or less than the mid value. So in my case, what do I see? I see the first case, which is that my ARR mid is actually looking at what? My ARR mid is, what is the value? 7. Okay, so my mid is here. So my ARR mid is less than my target. My ARR mean is less than my target. Right? So if ARR mean is less than the target, that means that the target, see, ARR mid is less than the target. So if this is the case, if this is less, the entire left portion is less because it is sorted. So discard this. How can I discard this? How will I discard this? Just move this L here, because this L has no point being there because it is a discarded thing. Move it 1 point after the mid. Right, so move it 1 point after the mid means L is equal to mid plus 1. Move it 1 point after the mid. And then we have case 2. Case 2 says ARR mid. So once we have done that, let us see if case 2 comes up. Okay, we will try to do it through the dry run itself. Let us do the dry run. Right, so in the dry run, the next item is that L has moved. So L has moved to where? L has moved to 8. So I have moved my L from here to here because the left side I have discarded. Right, so then my left side is discarded means L is moved to 8. Then my right is at 14 and my mid gets calculated new, which is 8 plus 14 divided by 2, which is 11. So my mid now moves to 11. That is, my new array now looks like this. So my new array now looks exactly like this. This is my new array. This side does not exist for me at all. Right? So this is my new array. This is the mid of that new array. Now again I will do the same thing. Now what is the case here? Is 39 wherever I am, ARR mid is 41. Is 41 less than target? 41 is not less than target. So I need a new case. So ARR mid is greater than target. So 41 is greater than target. Then what do I do? If 41 is greater than target, just imagine the situation that if my 41 is greater than target, then my element cannot exist here. Because 41 is greater than target means everybody else will be greater than the target. My element cannot exist here. I will discard this entire thing. How do I discard? I will bring R here. Right? I will bring R here. That way, what will happen is R will be equal to mid minus 1. So that is how I will discard. So R comes here and my mid gets automatically calculated. So R, my L is still at 8. My R comes at let's say 10. Yes. And my mid is calculated as 9. So my mid comes here. So that is my new array. So these are non-existing now. So after the second iteration, this is how this looks like. So what is my new array? My new array looks like this. So I had discarded this portion earlier. Now I have discarded this portion. So every time the new array getting discarded into smaller portions, and finally we will end up with the item itself. And then now if I see this, again what will happen is I will check these two cases. What is my mid? 36. Okay, ARR mid 36. 36 is less than 39. 36 is less than 39. Right? So 36 is less than 39 means that anything that is to the left of 36 is unimportant. 36 is less than 39. So everything to the left will be also less than 39. 39 cannot exist there. Right? So that means it will be to the right. So somewhere here is where the array target resides. It's what is coming out. And what do? We will therefore take L to the right of mid. Right? We will take L to the right of mid because L is equal to mid plus 1. That's why we are taking L to the right of mid. And that's where now what it becomes is this goes off. This becomes L. And mid gets calculated to, so L goes at 10. R is already at 10. Mid is calculated as 10. L plus R divided by 2. So this mid also goes here. The mid also goes here. So mid actually is here. So if mid is here, now you see, now wherever ARR mid is equal to target, not less than or greater than, it is equal to target, you need one more case then. So if ARR mid is equal to target, then you will return mid. That is, this is my position where I found the element. Right? So this completes your, and here is where you will have an exit. Right? 39 is equal to ARR mid, hence it will exit. So this completes, and this is exactly what you see. These are the three cases that I discussed. These three cases you see here. And that's your binary search algorithm. Now what happens internally is a binary search tree. So if you see this particular example, with this we will calculate the complexities of binary search tree, is that this entire tree is a binary search tree, right? So this entire tree is a binary search tree. You know binary search trees, but we will visit binary search trees tomorrow, or rather day after. And in that, in fact, tomorrow we'll visit binary search trees. So what we will see then is that any node on the left side, every node, every descendant will be greater than the particular parent. Every descendant will be greater than the particular parent. Any node you take, the descendants will be less than the parent and greater than the parent on the left and right side. So the left side will be always less than, the right side will be always greater than, which we all supposedly should know by now. Here also, if we take a single child like this, left child will be always less than the parent, right child will be greater than the parent. Whatever level you take all the descendants, it will follow this rule, right? So that is your binary search tree. Now in this binary search tree, this is exactly how the tree was divided or can be divided when we are actually dividing things. So 27, if we divide it at 27, my left array looks like this, my right array looks like this. So if we figure out that my element 39 is to the right of 27 because 39 is greater than 27, then I can discard all of this, right? I hope you are understanding. Then 41, when I'm at 41, I figured out that it is less than 41, then I can discard all of this because they have no meaning for me. Then I go here and at 36, I figure out that it will be on the right of 36. 39 is to the right of 36. I will discard this, and here I will find out that it is exactly equal. So these are the 4 iterations that I did. First I went here, second I went here, third I went here, fourth I went here. These are the 4 times I compared, right, that whether I exist to the right or I exist to the left of that particular parent, right, and accordingly I moved forward. Now if I have compared it 4 times, right, then do you think that to search 39 or 35 or 24, any leaf node like this, every leaf node will be searched at 4, or every leaf node will be searched 4 times actually to reach it. So if I am searching for 10, I will still take 1 iteration here, 2 iteration here, 1 iteration here, 2 iterations here, 3 iterations here, and 4th iteration here. Yeah. So I'll still take this many number of iterations. So first iteration anyway I have to compare with 27. Second iteration anyway I have to compare with 18. Third iteration here. Fourth iteration I'll have to compare with himself, right? Whether I am equal. So that is also 1 iteration, right? So 4 iterations I will anyways need for any leaf node that I am actually supposed to search, right? So then leaf means what? Leaf means that this is the worst case situation that can happen. 4 is the worst case situation that can happen. I could have easily done things in 3 iterations if it was here, or 2 iterations if it was here, or 1 iteration if it was here. So if it is 4 iterations, then it is definitely something which is worst case. So the worst case is actually 4 iterations and in that 4 iterations, if we say that 4 is the worst case number of iterations, again we have to come back to the situation where we say that in order to express any asymptotic notation, we have to express it as a function of n. I cannot just say 4 because 4 is for what? 4 is for 15 elements. Here there are 15 elements, right? If it is 150 elements, will it be 4? No. So we have to generalize it in the form of n, right? So that generalization, if we consider 15 as approximately 16, for again 2 things. 1, for an calculation ease, as well as 2, as I said, the number will be huge. So 1,50,000 has nothing to do, or will have nothing to do with, or nothing significant to do with just taking off 1 or adding 1 to it. So that way adding 1 doesn't create any sizable difference as far as asymptotic complexities are concerned. So if I can take 15 as 16, these 2 things is helped. 1, calculation sake. Second, I am not doing anything wrong because this would have been a large number. This is a theoretical understanding, hence we are taking 15. So 15, if it is approximately assumed as 16, that means 4 can be derived from 16 as 2 to the power 4 equal to 16. Why 4? Because we started off with 4. This is the 4. I am trying to prove that the worst case 4 number has something to do with 16. So that something to do with 16 is this. 2 to the power 4 is equal to 16. That means again take log on both sides. Take log on both sides, it becomes log base 2 of 16 is equal to 4. 2 to the power 4 equal to 16 would mean 2 to the power 4 equal to 16 would mean that taking log on both sides, 4 is equal to log base 2 of 16. That is what it means. So 4 is equal to log base 2 of 16 means the total number of times worst case will go, which is the left side, is equal to log base 2 of total number of elements. That means it is log base 2 of n is your complexity, right? You are supposed to find what is your left hand side. So left hand side says 4. I want to generalize 4. And 4 generalized came as log base 2 of 16, which is log base 2 of n. Right, so that is why my worst case complexity will be log base 2 of n. My average case in this case will be, as I told you, average case is take all the individual searches individually and assume that if you would have done that search individually, how much time will you have taken? First item, if you would have done that time. So first time, if you would have, let me remove this. Yeah, so the first time, if I would have searched for an item 27, then how much time would I have taken? I would have taken 1 unit of time. So at level number 1, I am taking 1 unit of time at level number 1, right? And at level number 2, I could have searched for this. In that case, how much time would I have taken? I would have first searched in 27, not found it, come here, searched for it, found it. So I would have taken 2 units of time. Similarly, I would have taken 2 units of time if I would have searched for this. So I am getting what? I am getting 1 at the first level, 4 at the next level, 12 at the next level, 32 at the next level. Why 12? Because here I would have taken 3 units of time, 3 units of time, 3 units of time, 3 units of time. Here 4 units, 4 units, 4 units, 4 units, and so on and so forth. So add it up, you will get 49. You will get 49 units of time. And 49 is for what? 15 elements. 15 elements means what? Divide it. Means average complexity, right? Or you have to take the sum of all and divide it by the total number of elements. That's what is the average case. So divided by the total elements, which is 15, you get a ceiling of 3.2, which comes to 4. So again you get 4. Here also you got 4. And here also you are getting 4. So now 4 converted to n will become the same. Na? Log base 2 of n, it will come only. Na? It will not be anything different. If it is 4 for 15, then what will it be for n? Log base 2 of n. Right? So that is the answer. So asymptotically it will be order of log base 2 of n. So both worst case and average case for binary search is log base 2 of n. And needless to say, my best case is order of 1, where I find it there itself. Not because it is the first element, I will always hit it with constant amount of time. Every time I run it. That is why it is order of 1. That is binary search for you. So between linear search and binary search, we have the precondition, which you know, right? This I'm sure you are now by now you know, and we do it sequentially here. We will half it. This one we have discussed at length. You can write it down, right? So we can write down what is the average case, worst case, time complexities for, and space complexities also. Both of them will require the search space complexity, which is an iterative space complexity of order of 1. And we use typically linear search when? We use linear search when they have a small unsorted data, right? Unsorted data is very important. Unsorted or sorted, linear can work, but small is also important. If it is large, you have to keep on dividing, because think about it. You have a time complexity of order of n. You have a time complexity of order of n, right? Now, if your n is large, then the time complexity is much high. Now compare it with log n, right? Let's say 16 is my n. So 16 times I have to search in a linear search. Log n, log 16 is what? 4. So then 4 times I have to only search for binary search. So compare 16 with 4. So this is for linear and this is for binary. Same number of elements. Here also 16 elements are there. Here also 16 elements are there. But my worst case looks drastically different. As you go up, the worst case will look drastically different with large number of n's. Hence binary search has to be done with a large sorted data, where I can definitely put a use case of binary search as the best possible search algorithm that can be used for large amount of sorted data. So that is on linear versus binary search. So before we move on to stack, let's do one more quiz. Let's come here. Let me see the question board. Any questions? Guys, I was happy with your interactions in the morning. I forgot to tell you. So keep interacting like this. If user puts an unsorted array in a binary search, then should we add an error condition for not putting sorted array, or add a simple sorting algo to fix the user's unsorted array? It depends. Like if the user has given you the flexibility to play around with that array, then it's okay. You can create a sorted array, because you can add an error and send it back to the user that you did not ask me to play around with the array. You just I was expecting a sorted array. Normally there will be an agreement between the user and the developer that my parameter will look like this and it will have this. So he will tell you, he or she will tell you that it will have a sorted array or an unsorted array. Your job is to take that and complete it. So that is the answer to that. Next is, there was a question like big O n log n is associated with divide and conquer, merge sort has n log n, but binary search has log n. There was a question like big O n log n is associated with divide and conquer. Okay, what is that? Big O n log n is associated with divide and conquer what? Search or sort? You are talking sort here, Deyanshu? Not understanding the question, Deyanshu. Deyanshu, put this question for discussion on our free time. I will give the Google form to type this question. Don't forget this question, please keep it. I keep on telling all of you, the questions I am telling you to park for us to discuss during our free time tomorrow or day after, I will forget, but you don't forget, please. I want to actually, this is the exact reason why I have kept some time to discuss all of your doubts. And thank you for posing these doubts. Okay, so Deyanshu, I have already answered you. Please keep this question aside for us to discuss in our discussion tomorrow or day after, right? So don't forget to use this question. What if the same element in sorted linear array? Partho, I didn't understand, sir. What if same elements in sorted linear array? What does it mean? It means that if you already have a sorted linear array, then what kind of search will you do? Is that the question, Partho? Can't we implement binary search using linked list? Because in linked list we cannot have random access. So what searching is implemented here? Binary search can be implemented anywhere. It doesn't depend on the data structure. So binary search, 1 minute, I am getting too many messages now. Okay, so binary search is not restricted to any kind of a target data structure. Binary search means take the data structure and start dividing it by half. Typically you do it in a linear data structure. So you can do it in a linked list, because linked list is a linear data structure. You cannot divide a stack or a queue. That's why nobody does it on that, because stacks and queue don't allow you to divide principally. So the 4 data structures which are there in linear data structures, binary search can be done in 2 of the data structures, array and linked list. So that's the answer, Samprapta, to your question. Shayan, duplicate input in the array. Duplicate input in the array, yes. So if there are duplicate inputs in the array, Shayan, there are 2 ways to handle it. Either you move it or don't move it. So if you see that 2 elements are matching, then sometimes you will move it, or one logic says you may move it, one logic will say you don't move it. Neither of them is correct or wrong. So it doesn't matter to sort an array which is already, let's say, the same elements. So if it is the same element, you might, conventional logic says that you will move. Non-conventional logic says why waste CPU cycles, don't move. So that way, whatever you do will be correct in terms of the same elements being in an array. Duplicate input, same elements. Yes, I answered that. Shayan Partho, I think I have answered that. Doing binary search on a linked list, we would have to traverse to the middle as it is. Yes, you'll have to traverse to the middle, and for that you'll have to maintain a special pointer, just like we maintained a special pointer, right? In array, did we know the middle? We didn't know the middle, we calculated the middle. Similarly, in a linked list also, we will calculate the middle. We will know the total number of elements, and accordingly we will calculate our middle from a linked list standpoint, and that calculation will be just a number. So we will now need to traverse to that number, because in an array we have a direct addressing. We know the number, we can directly go there, but in a linked list, knowing a number or a position is not sufficient, right? So we will have to go to that number from the beginning of the array or from the end of the array. So if we find out from a 10 pocket linked list that 5 is the midpoint, then 5's address we don't know. So from the head we have to go following the skipping of 5 nodes to actually reach there. So that is an extra effort or extra cost that will be put. There is no shying away from that, right? But if you are saying that the flexibilities that you will get once the search is over gives you much more benefit than an array. For example, search and insert. Search and insert, if you do in a linked list, it is much more easier. If you do it in an array, it is much more difficult. So depending on what your final outcome is with the search, you will have to define your data structure, whether it should be an array or a linked list. Right, so now, so ketchup night, that's the answer to your question. Yeah, so not exactly ketchup night. What will happen is, if your last question says, or last question says that even to calculate the number of elements, we would have to traverse entirely, losing the log, using the log n complexity. That gives you an n complexity. I understand what you are saying. We are not going to do that. The total number of elements in a typical scenario where an array, or sorry, a linked list will be used for binary search, is an entity that is a separately stored as and when you start inserting the linked list. So whenever you start inserting the linked list, there is a top counter that is maintained to understand how many nodes you have in the linked list. So you are not using a separate for loop to actually calculate the total number of elements of the linked list. Because you know this linked list's total number is so important, at the time of creation of the linked list, you will increment a global counter, and that will be your total counter. So that is a trade-off that you do, that you store a space complexity, you bring in a space complexity of n, sorry, not of n, of order of 1, just to counter the logarithmic complexity of traversing the link, or the n complexity of traversing the linked list to get the total number of elements. Right, I hope I have been able to explain that to you now. If at all there are some more questions, please keep on posting it, and I like the way of interaction that is happening, guys. You are asking good questions, you are asking interesting questions. If at all some explanation is not hitting the right chords, please ask it again. I will explain again. Don't worry about that. Right, so let's move on. Let's move on with the quiz. Okay. So we were doing searching. Here is searching starting now. Yeah. Sure. Come on. Quickly. Where are all of you? Going to joining? What's happening, guys? Oh, my bad. I was on the other screen, right? Yeah, now you can see. at present 113. Okay. Another 2 more we'll start. One more. Good. Let's start. Priyanshu, Deyanshu, Angad. Good. All the 3 names I have seen earlier. 78% accuracy. Very nice. Only sorted list. How come? Linear search is not for sorted list. It can work for sorted list. Unsorted list doesn't matter. So, sorted list is only for binary search. Next question. Still 9 of you answered this incorrectly. Leaderboard has changed completely. Asifur, I am seeing you for the first time. Good. 78. 9 of you answered low plus mid by 2. Probably typo. You cannot be not understanding this to that extent. Low plus mid by 2. No. Low plus high by 2. Next question. All of you please get this correct at least. Still 7 of you got this wrong. What is happening? 5 of you jumping to random index. Random fingers, is it? Jumping to random index. Come on. You will not give me a 100% accurate class. So many. 14. Order of n log n. Where does n log n come? Who says n log n? Did I teach you just now n log n? 14 of you answered it without even understanding my teaching. With some preconceived notion n log n. N log n is never there for a search perspective. It can be there from a sort perspective, not from a search perspective. Probably you mistook that. Pratyush Singh, I think I'm seeing your name for the first time. Good. Akib, good. You are coming back again. Now let me see what answers you have produced. Middle is right, but then still 60%. Why? Target. Okay. By comparing the target to the target element. Some people have answered that. By comparing the target to the sorted element. There is no sorting here. Middle element is what you are comparing. Always target is compared with the middle element. We are trying to search from a sorted array. Middle spelling is wrong. That's why some of you didn't get the percentage. Anyway, that's the quiz. Let's see what is our score. Abhinav, very good. Arpan and Arunima, very good. All three names I am seeing for the first time. Okay, the class accuracy is 72%. That's okay. Let us go on. We start off with stacks now. So on the stack front, what we'll do is, where is stack? Okay, I was just watching the fun on the chat window. Fastest fingers ruined ranking. Scam कर दिया. क्या हो रहा है लीडर बोर्ड का लास्ट में? Camera off. Oh, somebody called me.
1 minute.
Thank you for reminding that camera is off. Okay, chalo, let's start off. Where are we? Here. So, stack, first of all, the question that typically comes is around ADT and stack ADT and all of that. Now, there will be various definitions that you will get about ADT. And some of the definitions will be very crazy definitions, right? And I'll probably explain you in a much better way the definitions of ADT or definition of ADT that you actually should stick by. So the definition of ADT is that, first of all, you have to understand that we create something for somebody else means that that created product has some features, right? Those features are something that that person need not know how it is built. We do not know how a TV produces, let's say, brighter light versus contrasting light. We do not know that, but we use that feature. So inside any data structure, if we start using features of that data structure without knowing how it is being done, so we only know the what part of it but don't know the how part of it, then that data structure is called as an abstract data type. So an abstract data type is where the what the operation to be performed is known but not how the operation is to be performed. Therefore, the operations that can be performed, for example, in a stack are the push, the pop, the peek, the isEmpty. Those are the operations that can be performed in a stack, right? So those operations we do not know as consumers of the stack. You have created a stack algorithm. I am using it. I do not need to know how you created a push, how you created a pop. I'll start using it. That is exactly what an abstract data type means, where an end user does not need to know the implementation details of the feature that is being provided. So that is an abstract data type. That is what is defined here. Now, a lot of you have approached me and said that how do I remember so many functions across so many data types that we have learned? Stack, linear queue, circular queue, DQ. So many data types, so many functions will be there across these abstract data types. So my suggestion to you is, if you see this table, remember five functions: insert, delete, peek, full check and empty check. Insert, delete, you understand, right? Everything will have an insert, delete. And then peek is something where you are just doing some chori, right? You are not taking it out but just trying to view something from behind the scenes. So that also I hope you will remember. And then the two things, the boundary condition checks, which is empty and full, both the things you will have to check. So the 5 functions I hope you will remember, right? So these 5 functions, if you remember that these 5 functions should be there, then from a stack perspective, it will be push for insert, NQ for linear, NQ for circular, right? So this part, if you see, is the same for the top 3: stack, linear queue, circular queue, which we will do today, right? So all of these is the same. We will do the same set of functions: push for insert, pop for delete. In linear queue and circular queue, we'll do, instead of push and pop, we'll call them as NQ, DQ, but functionality is the same. Push is insert and delete is DQ, right? And for peek, there will be a peek for all 3 of them. Is full is the same, is empty is the same. So from a stack and linear queue and circular queue perspective, I hope you can remember. For DQ, which is a double-ended queue, because it is double-ended, the insert will happen from both the ends, right? So insert will happen from both the ends, means insert front, insert rear, delete front, delete rear, because both the ends are now open. You can do both the operations from both the ends. Peek also therefore can be done from both the ends. And full and empty is full and empty, it need not have both the ends. Na? So DQ is like that. Linked list, double linked list, same as DQ, because it is open from both the ends, right? You can do a beginning, you can do an end, and additionally you can do at any pause, any position you can insert, any position you can delete. So that's the way to remember. So I'll just summarize 5 functions: insert, delete, peek, check full, check empty, right? So these are the 5 functions you have to remember. All the data types are here. Now the first 3 data types, stack and linear queue, till the time you are not allowing both the ends, right? Both the ends, till the time you are not allowing. Stack doesn't allow both the ends, linear queue doesn't allow both the ends, circular queue doesn't allow both the ends. That is, insert and delete is not allowed from both the ends simultaneously. So till the time that is happening, then you use push, NQ and DQ. Pop, peek will anyway be there, is full, is empty, anyway will be there. That I don't think you have to help remember. Then the DQ, linked list and double linked list has both the ends, hence increase the functions by 2. So if you are doing insert, say insert front, insert rear. If you are doing delete, delete front, delete rear. If you are doing peek, peek front, peek rear, and so on and so forth. That's how I think this table might, anyway, whoever needs it, whoever doesn't need it, skip it. But if you need it, I just thought I'll create this for you. So the next thing is something on the stack where we see that the functionalities all of you are aware of, but still I'll go through it quickly. So if you have a stack like this, then when you are doing a push operation, top, which actually is very important pointer from a stack perspective, is at -1. It's a pointer which points to the for an empty stack, it will always point to -1. So when you are pushing an item into the stack, then what do you need to check? You will need to check first whether the stack is full. So whether my top is actually equal to my max size -1. That is what you need to check, right? My max size is max size is, let's say, 5. Top is index based. So top has to be equal to 5 minus 1 for it to be full, right? So because top is index based and max size is count based. So top will be equal to max size -1 when it is full, and hence it will return false. So if the stack is full, then I will print an overflow, and then I will enter into the actual process, or rather else I will enter into the actual process. Actual process is what? I will push it here. That means my top will be top +1. This will be top +1. So top will now come here, and here now I get access to this location of that array or that linked list or whatever we are doing, right, to maintain this stack. So top +1 it will become, and then at this top +1 I will put my data, let's say X. So that is what this particular algorithm is. For the pop, if let's say X, Y, Z I have, and my top has moved here, top is now pointing here. Now what I will do is, my top, wherever my top is, I will take out that element and bring it or return it outside to me. So what I will do is, First, I will need to check whether I at all have any elements. It could be that my list is empty. So if my list was not here like this, then I will say is empty, then print underflow. What is empty? My top will be here. Top will be -1 if it is empty, I told you. So if top is -1, then is empty. Right? So top is -1, then is empty is fine. Then is empty will print underflow. Else, what I will do? I will take out this element. Take out this element means I will put it inside a variable, and then I will decrease the top because this is no more the top. I will decrease the top, and that variable I will return out to the caller. That I will do. What happens if I would have taken this syntax above this? Then what would have happened is top would have been decremented first. That means you would have brought back top here, and you would have lost access to this element because top now points here. So how can you pop 2 now? 2 you cannot return. So take 2 first, which is pointing to top, then decrease top, right? That sequence is very important. And for peak, it is the same thing as pop. Only thing is you are not changing the top. This top you are not changing. All you are doing is returning the stack top, which you are putting it inside X. Now you don't need to put it inside X. You just can return it directly in the peak part of it. So that is on the stack operations. Now, if I see the applications of the stack, then one of the important questions that comes is how can Aman is saying too much lag. Aman, is it the lag on the video you are complaining about or the quiz? If there is a lag in the video, tell me, because I can't understand the lag. Typically, it will be a 10 to 15 seconds lag between my speaking and you hearing me. Okay, fine. Let's move on then. So what I'm trying, and this thing you will not find in most of the books, right? This is something we would have taught you during your C days, and this is something I wanted to touch upon. This is your favorite factorial function, and we have been asked that what is recursion and how does stack how stack is used in recursion. Explain us how stack is used in recursion, right? So it's not saying find out the factorial using stack. That's not the question. It is saying how is stack used in a recursive function. You can take, for that matter, any recursive function. You can take a power, you can take a factorial, you can take a Fibonacci. All of them will have the same effect in terms of usage of recursion. So what we will understand now is how is stack typical, unless you have already understood from your C days, how is stack being used in recursion, and we will try to draw the stack as we move along. So what happens is, let's say top is here. Let's say my top is here, -1. And let's say this is the first layer of the stack. Now I have 2 functions here, main and factorial. There are 2 functions. Now every function, in order to execute whatever it has to do, it needs 2 things to do. One, it needs the parameters that it is given with. For example, here you are given with void parameters, which is okay. Second thing, it needs internal variables memory. So here it has assigned n equal to 3. So it needs to store n equal to 3 till the time this entire thing goes on. It needs to have access to that n equal to 3. That n equal to 3 memory that is given by the compiler cannot get lost. By the time this gets over, then only it can get lost. In between, it cannot get lost. So a function needs 2 things. One, memory to store parameters, memory to store internal variables. So it goes to the compiler and says, I am main, I want to execute myself, I need some memory. So main compiler says, okay, you need memory, I have a stack, and this is typically your RAM, right? I have a stack, come to me, I will give you memory. So main comes here and starts reciting. Top gets allotted here, right? So top gets allotted here, and main gets some memory here in terms of both the parameters as well as in terms of the internal variables that it needs. So main gets some memory here, right? So this entire area is mains. It will use this stack. Now main says at some point that I want to call a function. This is a factorial function. So the compiler says you want to call a function, then my entire control will go to that function. The entire CPU will start now working towards factorial function. Main will not have a CPU share. Main says fine, don't have a CPU share is okay. But when I need it back again, I would need my memory again. So whatever memory you gave to me here, needs to be here. Don't release it. Don't release this space, because I'll come back here once you give me control back. So main says do this. I'm calling factorial, give control to factorial, but store my memory in the stack. Compiler says okay, I'll store your memory inside the factorial, inside the stack. And what happens is, from here main actually makes a call. Main actually makes a call to the factorial function. So the factorial function says again the same thing. Factorial needs what? 1, the parameter. 2, the variables internally that it may use, right? So internal variables. So factorial function says to compiler, I need what? I need memory. Compiler says come, I'll give you a space. Top moves up, right? And it gets some space. So it says that okay, fine, thank you, you have given me some space. Now I am what? Let's say factorial 3, right? So I am factorial 3. So that is what is the actual function that gets called in the first instance. Now factorial 3 will say, I know what I am doing. I know I have to do 3 star, and I have to actually put a placeholder where the call of factorial 2 will return. So let me call factorial 2. So then it calls factorial 2, but it goes to main before that and says, main, I have stored something here. Please don't release it. Right? Please don't release it. I have stored something here. You use it. You use the rest of the memory for whatever you need. Main says fine. So it calls factorial 3, factorial 2. Factorial 2 again says the same thing to main, that I need some memory. Okay, you need this memory. Then factorial 2 comes here, resides here. And then factorial 2 says, I know that I have to do 2 multiplied by whatever factorial 1 will return to me. So let me call factorial 1. But before going there, it goes to main and does the same story. Right? So then again, main starts here. And here what happens is factorial 1 comes and says that I need some memory. So factorial 1 comes here. So factorial 1 comes here and then says that I know what I have to do. I need to return 1. That is what factorial 1 says. So factorial 1 returns 1. 1 comes here. This top which was here gets reduced to here. Right? And then this is therefore no more there. This is freed and given back to other execution engines or other executables. Right? So this 1 comes here. As soon as this 1 comes here, this factorial 2 says, okay, I am also over. 2 star 1 is 2. Let me return this. So 2 star 1 is 2. It returns this here. And that means that this is also over. This memory is also getting released because top will now move here to this. And this 3 star 2 will say, I know I am over. 3 stars 2 is 6. As long as I can give back 6, I will give back 6. So this goes here, wherever main was. So main would have expected a call. So the call comes here. And this call is printed or whatever is done, and then main gets over. When main gets over, this memory is also released and top comes back to -1. So that this process, when we actually were building the stack, is called as stack winding. And the process when we were coming back and releasing the stack is called as unwinding. Right? And this is how recursion works. Every recursion function, each and every block of that function puts some memory in the stack and goes on to the next function. Puts some memory in the stack, goes on to the next function. This is how it happens. Therefore, it is commonly said that avoid recursion if you have less memory. Do iterative programming. If you have less memory, do iterative programming. Avoid recursion. Right? So I hope that is something that is understandable, and in case you are hearing this for the first time, I hope it makes sense in terms of how a stack is used in order to store data or in order to help you with recursion. Now, the applications of stack. What is a stack additive? We have discussed. Explain its operations. We have discussed. Both of these we have discussed. Now, this is a simple case. Let me put it on the quiz window. Who can answer this? What is the answer of this? I hope you are doing it. This is simple stack operation. Devanshu Raj says 22112. 22112. Devanshu, that's not even an option. Oh, it is an option. Sorry, Devanshu, you're right. It's an option. I missed it. Okay, all of you are answering it correctly. Fantastic. So I don't need to probably explain much, but just so that we are here, we will just complete it. We did a push 1, then we did a push 2, then we did a pop, so 2 comes out. Okay, next we did a push 1, then we did a push 2, then we did a pop, so 2 comes out. Then we did another pop, 1 comes out. Then we do another pop, 1 comes out. And then we do a push 2 and a pop. So 2 is pop, 22112 is the answer. So thank you for that. Okay, so Zeniki, I hope you have seen the answer now on the screen. Next, stack can be implemented using. Can you answer this, guys? Stack can be implemented using. Stack can be implemented using push pop. No. Push pop are operations of the stack. They are talking what data structure will you use to implement a stack. Stack is a data structure implemented through another data structure. Array and linked list is the correct answer. Islamic talks, what is this null? Stack can be implemented using null. Okay. In case you wanted to say something else, Islamic talk, please feel free to write it out. Which data structure is used to implement recursion? We know that. We have just now discussed that stack is always used to implement recursion. How it is used, I have explained you just now. So that's on stacks. Let me see if there is a separate quiz on stack. Then we'll do that quiz. Yes, there is a quiz on stack, so let us do that quiz now. Okay, we'll do a quiz now. We will close this off. Chalo, let's start off. Look, it is shared, right? Yeah. 90 we start. Okay, let's start. (81) 80%. Shayon Orignam Bhavya Rai, new name, good. 82%. FIFO, whoever has done, I'm sure you were confused. Stack is last in, first out. If your top is pointing to wherever top is pointing, you can only take out that. That means top will always point to the top and you can always take out the top. Right? So that way it is first in, last out, or you can say last in, first out. So that way LIFO is the right answer. Next. Shayon Showan Bhavya. Yeah. So there is two ways of interpreting bottom of stack. Now people who have answered bottom of stack, I understand from where you have answered this. But bottom of stack really means bottom. It does not mean where the stack is right now. If the stack is full, will you say that is bottom? So you are saying my bottom, I will always insert wherever I can see the last top, right? I will increase the top and insert it. So if I am midway into that container, that stack, imagine it as a container. If I am midway into the container, will I treat that midway as my bottom? I won't. Bottom is bottom. So it's not inserted at the bottom that way. But I understand why you gave this. So just rectify that thought process. Okay, 69. What happened? Stack underflow occurs when pop is attempted when top equal to -1. Yes. Unless a pop is attempted, how will underflow occur? Top equal to size -1 is not an underflow. Let's say my size is 5. Size -1 is 4. Top equal to size -1, it is at the top of the stack. How will underflow occur? That is overflow. And that overflow will also not occur if you actually start pushing an element. So you have to push an element for an overflow to occur. Here they are talking underflow. So pop an element when top is -1. So 69 is the answer. 23 of you, it is a confusion, I can understand. But please rectify this. This is a basic concept of stack. If you are not clear, please ask me again. After Sunday, don't have any problems. Good. 86. Leaderboard doesn't change much. I'm surprised. Shayon, you seem to be appearing in top 1 every time. But overall, you don't appear. I don't know what is happening. Let me check the results also. The element currently at top. Yes, that's the answer. Last question. Sohan, Shayon, Pratyush. Not an application of stack. Function calling is an application of stack. Parenthesis is an application of stack. Expression is an application of stack. Discra is not an application of stack. So please remember these. Expressions evaluation means if I give you an expression that you typically will type in a calculator, let's say bracket 6 plus 5 equal to, or 6 plus 5 star 3, again bracket close, again another bracket open, that kind of a complicated expression, it's also evaluated using a stack. Parenthesis matching, the first bracket, second bracket, third bracket should match with the corresponding first bracket, second bracket, third bracket is also a part of parenthesis matching. I have explained all of these in my lectures which are available for you to probably see in the Code to Win channel. Unless you have not already seen it, people who don't have access to the channel, I'm sure you will get access, otherwise I'll anyway post it out. Please have a look at it. We cannot complete everything here, but then function calling, parenthesis and expression are functionalities. I thought recursion is the most important thing for you to know as the application of stack, which is why from an application standpoint I've explained you recursion. Let's see the results of the quiz. Orunima, Orpon, Avinav. And at least 3 questions, Shayon, you are at top. Why you are not at top here? I'll have to see this. Something is wrong. Overall, something is happening. Okay, chalo. We will start off now with the next part, which is expression, notation. Yeah, so final leaderboard doesn't seem to be correct, will be a wrong statement to make, because this is a professional tool, which is a paid tool. So they would have done all kinds of algorithms to create that leaderboard. We might not be knowing the logic. Once we know the logic, you'll understand. But we will see. I'll anyway aggregate and I'll see. Zeniki says it gives priority to caps lock names. Shayon, make your name caps lock. You'll get priority. Okay, chalo. Next. Notations. Let us visit notations now. Now, notations is very important, because typically one question you can expect, either infix to postfix, or from a postfix evaluation perspective, you will typically expect one notation conversion. So we will do many problems in notation, because that is a strong area which you should score, and I'll try to do many problems that I feel is important. But for doing those problems, we need to remember this table, right? So one is that this is the precedence table. You would have seen this from your C days. Highest precedence is your brackets, and the next highest precedence is your dollar, is also expressed as exponent. So sometimes you might see dollar, sometimes you will see exponent. Both of them are the same thing. And then you have the star, slash and modulo at the same level, plus minus at the same level. So this is called as precedence. This is called as precedence. And if any of these three appear in one expression, then who is going to happen first? That is called as associativity, left to right. So precedence and associativity have this meaning. I hope that is clear. Now let us try to solve this problem. Don't get confused or overwhelmed with the left side algorithm. Once you understand, left side algorithm will be very easy for you to write. Let us do this step by step. I will do both kind of ways. I will do it by drawing. Next problem I will do it in a table also, the way you should write it in the examination. So the first thing that you have to do, we are talking about what? We are talking about infix to postfix. First thing you need to remember is, why is everybody so hung up in converting something to postfix? That is, this is looking so good, infix, right? Every operator is having two operands on both sides, right? It is looking so good, we understand it. So why should we compare to postfix? Any questions, any answers in the chat window? Why are we so hung up and studying infix to postfix? I'm watching the chat window. Any answers? No one? Different priorities. Easier for the machine. Which operation to perform first? Okay. For understanding of compiler, for machine recognition. Most of you are giving the right answer, but I have not seen the why. Easier for the machine. Very easy to say. Computer can understand it very easily. Very easy to say that. I am asking why. Why does the computer understand postfix better? Do any of you know? Why does the computer understand postfix better? Farhan Anwar, excellent answer. Postfix is evaluated using stack, which is easier to implement. Yes. Now you can't just write an if else code and keep on writing if else, if else, if else, if else. Use a data structure to its advantage. In a postfix, just give it to a stack. It will come out with the evaluation of that result. But if you give an infix to a stack, it will not come out with the evaluation of the result. That's why conversion of that infix to postfix is so important. And we will see how we will convert a postfix to an expression or a result. But before that, let's convert first to an infix to a postfix, and then we will see. Yes, sketch at night, you are also right, ghost coder, because during postfix it helps to scan the whole expression at once. Yes, you don't need to go back. Those are the advantages, but the main thing is that it uses a stack to evaluate it. After that, whatever comes are the advantages. I was asking why. Okay, now coming back here, so what do? It's very simple. If you encounter an operator, this is an operand. If you encounter an operand, then append it to P. What is P? P is your answer. Append it to P. Start appending it to P, because P was your output. If you encounter an operator. If you encounter an operand, if you encounter an operator, then push it into the stack. If you encounter an operator, then push it into the stack. This is where it is happening. something else also happens inside this. I will explain that. Right, so this is also done. Then you have encountered an operator, so append it into P. This is your P, you are appending it into P. Then you got a star. Now start remembering your precedence table. Is star greater than plus? Remember this. If I am bigger than you, I can stay on top of you. If I am same as you or chota than you, I cannot stay on top of you. That is the essence through which you can remember this. So star is bigger than plus. If star is bigger than plus, then star can stay on top of plus. Then comes 5. You are getting an operand, move it out. Right? Then comes minus. Now minus has the right to come here, but is minus falling under this category? Minus is bigger than star? No. So minus says I want star to go out. So star comes out. So star is popped. Right? Then minus thinks that it can come here now. So this is now empty. This block is empty, so minus thinks it can come here. But here also minus cannot stay. Why? Because at the bottom there is somebody who is same size. Minus and plus are same size. Same size cannot stay together. So minus cannot stay with plus. Minus wants star to be popped out. Plus to be popped out. So plus gets popped out. So the entire stack now becomes empty. And this entire stack now minus comes into play. So minus now starts staying inside the stack. Then comes your bracket. When bracket comes, then just push it into when the starting bracket comes, push it into the stack. This is what is written here. When starting bracket comes, push it into the stack. Then comes 3. 3, you know where it needs to go. It's an operand, it needs to go there. Plus, when plus comes, plus can come above bracket. A bracket inside a stack is lowest priority. Please remember that. A bracket inside the stack is lowest priority. Right? So inside the stack it is lowest priority. Please remember that and make note of that. So plus can stay above the bracket. Then we have 17. 17 will come here. Then we have this bracket ending. So if you have a bracket ending, then you will have to pop out everything till you get a bracket beginning. So we will have to pop out this and this also and discard this because this is a bracket of no use now. So we will pop this out, plus will go here, right? And then these two are empty now. The entire stack is empty with minus here, so top is here, right? So that is how the stack looks like. Now we have star. Star can stay here. Star is bigger than minus. Star can stay there. Then comes 5. 5 is written out. Now the expression is null. I have nothing more to evaluate. If I have nothing more to evaluate, I will just pop out my stack. So star and then minus. So that is your infix to postfix conversion. So now you have a postfix expression of the same infix and this infix, of the same infix and this postfix that you just now got. Now put it into a stack and ask the stack to evaluate it. Stack will evaluate it immediately for you. So there are 2 times stack is used. If you give infix, first conversion to postfix, then postfix to the evaluation process of the postfix. That will also happen through stack. We will also see that after 2 examples. So let us see one example where we are converting an infix to a postfix. So here what are we doing? We are actually saying the same thing but without drawing the stack, because you might not have time to draw the stack. The stack might become dirty So you might be thinking how to represent it. Represent it in a table like this. All that you need to do is assume that one of your columns is the stack, and that is this column. Assume that this column is the stack, and it points in this direction as the top. So the topmost element is here, 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 here. These are your topmost elements, right? Assume that, and let's see how it stitches together, right? So let's see that. So if you I'll go through this step by step. Next example I'll go a bit faster because it's pretty lengthy to go through all the examples, but you will understand. If you don't understand, stop me. Okay, now when I say A, where will A go? A is going to the output. So either you have the stack or you have the output, the same way as we had earlier. Next comes plus. What is plus? Plus is an operator, so it should go into the stack. The output still has A, right? Next comes B. It's a operand, right? It will go to the output. The stack still has plus. Next comes star. Star will go on top of plus. It is allowed. Stack, the output still has AB. C will go to the output. Minus cannot come here because minus is smaller than star. So this star has to go out. So star is popped out. Minus cannot stay with plus also. So plus has to go out. So plus goes out. Now minus can have an empty stack to start residing. So that is where minus starts residing. Next you have D. So D will go to the output. Next you have dollar exponent, right? Exponent is highest. So exponent can stay above minus. F will go to the output. Slash says I want to come here, but slash cannot stay here because slash is lesser than dollar. So slash wants dollar to go out, so dollar goes out. Now slash can start staying with minus because minus is smaller, so slash can start taking on top of minus. Then comes H. H will go here, and that is the end. If it is the end, then you have to pop this first and then pop this, right? So that is how your expression through a table also can be evaluated from an infix to postfix standpoint. Now this I will go a bit quickly. Same thing, infix to postfix. It has a bracket, so let's be careful about that. A goes to the stack. A goes to the output. Minus goes to the stack. Bracket goes to the stack. B, output. Slash, it can stay above bracket. Bracket has lowest precedence, I told you. C goes to the output. Plus cannot. Plus wants to stay here, but it cannot. Why? Because slash is there. So that slash goes out. Now plus can stay here. Then we have bracket. Bracket will come here. D comes here. Modulo can go above bracket. Yes, modulo can go above bracket. Acha, you might have question, how can bracket go above plus? We said bracket have lowest precedence. How can bracket go above plus? Because the starting bracket, we said by default close your eyes and push it into the stack. No need to check anything. That is what we said. That is why brackets can go inside the stack. The rule is not applicable to a starting bracket. Brackets have a different rule because they are not treated, they are treated to aggregate things together. They have a different rule. That is the rule we are talking about here. And that way modulo, once it goes there, E goes outside. Then star comes. Star doesn't want this modulo. So modulo is coming out. Star now can stay here. Then F goes here. Bracket, okay, this is an end bracket. So what do we have to do? Pop everything till the first bracket. So we will have to pop this. We will have to pop this and discard it. We will have to pop this and discard it. right? So that is what we will do. Then we will have minus bracket plus, which is okay. Then we have slash. Slash can stay above plus, so which is allowed. G will go to the output. Bracket will mean that all of this will be popped along with this also. Then only this will remain, and slash will come here and plus will come here from the pop here. Then comes star. So star will go above minus. Then comes H will go at the end, and then comes end, which means the expression has ended. So this star will go here and this minus will go here. So I thought I'll go quickly, but anyways I explained it for you. I hope this is clear. Very easy. Don't miss out on scoring in this kind of a problem. This is the easiest problem that you can get. Infix to postfix, one more. There are three brackets rather. So push this element into the stack, which is the first bracket. A to the output, plus into the stack, B to the output, bracket, remove everything. Remove everything means plus will come out and stay here. Starting bracket will be discarded, right? So that is what this means. Star will come into the stack, C will go to the output. Then we have after C minus. Okay, minus will minus wants to stay here. So minus doesn't want star. So where will star go? Here. Then minus can stay. Then we have a bracket. So bracket can stay here above minus. D will go out. Minus can stay above bracket. E will go out. Bracket will pop everything till the bracket. So this minus will go here and this bracket will be discarded. So only minus will remain. Star will go above minus, which is allowed. Bracket will come here. Output of F goes here. Plus will come here because plus can stay above bracket. Bracket is lower in precedence. Output of G will go here. Then bracket comes. So you'll have to pop this plus and this bracket is discarded. Minus and star is left. You are ending. So the star and minus should come out here. So that is how we are representing the infix to postfix. We just went through 4 examples now. Now let us do a postfix evaluation. Here also I will be doing the stack drawing approach first, and then we will do the table approach. So here, this is where all the while we converted infix to postfix to do what? To solve that expression. So the solution never came, postfix expression came. Now the postfix expression will fed into this stack and we will solve it, right? The stack will solve it for us, and that is the beauty of asking for postfix. So what we will do is we will say that we will, whenever we get just the ulta of what we did earlier, right? We were getting the operand and pushing it at the output and the operator into the stack. Now we'll push the operand into the stack. So 3 will be pushed into the stack. 16 will be pushed into the stack. 2 will be pushed into the stack. And then plus is kept like this. And when plus is kept like this, it demands that 2 things come out because plus is a binary operator. It wants 2 items to come out of the stack. So the 2 items that will come out is 2. The first pop will go to the right hand side. Do not miss this. Otherwise your division subtractions will all be wrong. First pop will go to the right hand side. First pop will go to the right hand side. First pop will go to the right hand side. Please remember this. I don't want you to miss out and score not enough on this just because you made a mistake here. And then 16 will go to the left side. And that makes it as 18. Now push this 18 into the stack. Push this 18 into the stack. Now what is coming? 16 2 plus. So till this point we have done. Now star is coming. Star has come. Binary operator. Take out 2. Take out 2 elements. So 18 will go here. 3 will go here. Right? 8 3s are 24. 2 54. So 54 is your new item. Push it into the stack. Then comes 12. push it into the stack. Then comes 6, push it into the stack, right? And then comes slash. So slash has come, so take out 6, put it here, take out 12, put it here. What is the output? 2, push it into the stack. Then you get a minus. That means you take out 2 minus, you take out 2 from here and 54 from here. So you get 52 as your answer. So that is how you will solve this. Now if you see a stack table approach for that, getting 2, we will put it into the stack. Then we got 3, put it into the stack. Then we got 1, put it into the stack. Now we are getting a operator. So what is the operator going to perform? We will perform, we will have star and we will let perform, 1 will go to the right side, 3 will go to the left side. That is what is written here. Compute 3 star 1. Right? 3 star 1 is what? 3. So then push this 3 into the stack. So 3 and 1 were popped, 2 was already remaining, and this gave you 3. So you push this 3 into the stack. Then comes plus. So plus will mean that 3 will come out to the right side and 2 will come out to the left side. So you will get 5. So now push this 5 into the stack, because 2 and 3 are popped out, stack was empty, 5 goes inside. 9, push it into the stack. Minus means 9 will come to the right side of minus, 5 will come to the left side of minus. This is where I am saying don't miss out. -4 will be your answer. So that is on that part. Now we are trying to do prefix to postfix. Now prefix to postfix is going to be postfix evaluation. The way we do postfix evaluation, same logic. That is, we will take the operands into the stack. Same logic. But only difference is we will treat the entire expression from right to left. So our input to the stack will be starting from D. That's the only difference. Nothing changes. So D moves into the stack, C moves into the stack, get an operator. So you will pop out C. They have not written it here. So okay, so we will pop out C here minus D. Right? So this, when we do this pop operation, this pop operation of D minus C is something that we will have to convert into a postfix. To help you understand that there is one more step in between, when I said that minus will have to be put in between, that is, we were trying to do an infix kind of a problem. Now because we have been advised to convert it into a postfix, so we will do a postfix here itself. So instead of saying that we will do D minus C, we will say that it will be CD minus. Right? So it will be CD minus, because CD minus is going to represent your D minus C. Now when we actually go here, if you see here, this expression CD minus now becomes one complete entity. Right? It is one complete entity because it's a variable at the end of the day. I understand C and D, but C and D have been evaluated as CD minus. So this is no more individual C and D. It has become CD minus. So that CD minus is supposed to be pushed into the stack. So C and D is supposed to be pushed into the stack, and then comes your B. So B goes inside the stack. Then comes your A. A will go inside the stack. Then comes a plus. So A and B will need to be plussed. So that becomes AB plus. Since it is from the reverse side, it is not BA plus, it is AB plus. And likewise, this is also not DC minus, it is CD minus. That is the second thing that I forgot to tell you. Because you are going from this direction, there are two things that will happen. One, you are anyways going to do a postfix evaluation. but you will do it in a reverse direction. And when you get these situations of popping out two elements, then the conventional style of pop out that I told you, right to the right, and the first to the right and the second to the left, will be flipped, and you will create that postfix expression. Here also, if this is AB plus, then this gets pushed into the stack, and then a star comes here, and then star comes here means these two expressions will need to be starred, right? So typically in what we learned earlier, what would we have done? Star we would have kept top of this stack to the right, bottom of this stack here, next, not bottom, the next item we would have kept here, right? We will do the ulta. So we will do a ulta here. We will say this person I will take first. So CD I will take first. Sorry, we will do the ulta means AB we will take first. So AB plus is the entire entity. Don't forget, AB plus is your entire entity, not AB. AB plus is your entire entity. So AB plus we will take, CD minus is your entire entity. So we will take that. And then we will take star, which is the operand operator that we were actually working with. So these are the two things. Simple here also. All you need to be careful is work from the right to left, and when you are taking off from the stack, then take off the first element of the stack will come here. So in that sense, it is the left side, and the second element will come to the right, contrary to the earlier statement that I made in the postfix conversion. So since this is prefix to postfix, that's why this is contrary to that statement. What is the time complexity here? Each operand will itself take order of 1. Each operand, plus, minus, star, whatever it is, will take order of 1 to go into the output, right? Infix to postfix. So operands directly go to the output. Operator will be pushed into the stack, right? So my bad, I talked about operator here. So each operand, whatever it is, 7, 9, 10, whatever it is, will be going to the output, means single unit of time it will take, and that means a constant unit of time. Operator star slash, this will go where? Into the stack. How much time will it take? Again, constant, because I don't need to do any loops. Constant amount of time. Parenthesis, how much time will it take? Again, constant amount of time, right? So all of them are constant amount of time. Now when they get popped, when these get popped from the stack, how many pops will happen? There will be n pops, right? So if there are n pops to completely empty the stack, then the order will be order of n. So I will have to run a loop till all the n's are out, all the n pops are out, and that's why the time complexity from an infix to postfix conversion is order of n. While all the pushes will be 1 1 1 1 order, the actual exits will be all together, not all together. We'll have to run a loop to actually get all of them out, and hence we will have to consume order of n. That is why time complexity for infix to postfix is order of n. Reverse Polish notation RPN, it has come 2-3 times, so be aware of it. Now A plus B is we know as infix. AB plus is known as postfix. What is happening? The value or the positioning of this operator plus is defining whether it is inside post, this is post, or pre, That is how the nomenclature is. Now this is called as RPN, and this is called as RPN, and this is called as PN. So the Polish notation is actually the prefix notation. So prefix is called as Polish, and postfix is called as reverse Polish. Infix is infix. Remember that, don't confuse things. Applications of stack. Stack cannot be used to evaluate arithmetic expression, implement recursion, allocate resources, convert infix. See, we can do this. We know it can do this. We know it can do this. We know it can do this. So the only thing left is this. Evaluate arithmetic expression, we just now did it. Implement recursion, we know. Convert infix to equivalent postfix we have done. So only thing is allocate resources by the operating system. It cannot be used. What is essential for converting infix expression to postfix? This has come 2-3 times, so be careful about this. What is essential for converting? One, infix to postfix. What all do you need? Don't you need a stack? Of course. Don't you need the precedence knowledge? Of course. And don't you need the operands that you need to push? So whatever you need, just ask for it. Without having those as the input, you cannot complete that expression, complete that storyline. That means complete that expression evaluation. So those are the things that you will need. So with that we come to the end of stack. We'll start queues, but let's do a quiz quickly. Let's see if you can maintain above 70%. How is this chat window looking? Multiply, push a modulo outside stack. Srijib, multiply and modulo are of the same precedence. And I told you that if you are of the same size, you cannot stand on top of him or her. That is why it will push it to the there is nothing called left right here. Left to right is not applicable for pushing out. If you have 3 layers of or 3-4 things in the same hierarchy, then these 3-4 things cannot stay together, as simple as that. Whether left to right, right to left, does not matter. It has to be pushed outside. I hope that makes it clear. Okay, so star, slash, modulo, all of this, if any of this wants to stay on top of that, that person has to go out. This person wants to stay on top of this has to go out. Doesn't matter where they are located. I hope that answers Srijit. Okay, now we were discussing notation conversion. Chalo, let's see. What is Shayan going to do now? Shayan, you have changed it to capital. Chalo, come in. कोई जनगण How many are there? 104. 90 will start. Shayan has changed to capital, I can see. Come on, 8 of you. Eight. Okay, we'll start. Shayon Farhan Akib 63. Come on guys, infix notation you are not aware of before both the operands. Infix is inside two operands, that is in between, inside, in between. Pre means before, post means after. Please try to remember this. This is crazy. 14 of you. 14 plus 8. Come on. This is still good. Orindam, seeing you after some time. Farhan was anyway there. Shayan is there. Akib is still there. Samprapta Moitro, I am seeing you probably first. I don't know, within top 10, but good. I thought so, that you will have a lot of wrong answers. 47 of you have answered this correctly, but is it correct? I'll have to check this. Postfix, both infix and postfix, does not require parenthesis to preserve order. Yeah, it to me appears to be C, but most of you have answered postfix. So I'll have to check this answer. Again, I have to give marks to both of it if it is correct. Both infix and postfix should, in fact infix, okay, I was thinking prefix, my bad. Okay, then postfix is the right answer. Infix definitely requires brackets, right? How else would you evaluate normal human being expressions? Normal human being expressions are with brackets, right? So if you put infix as not requires, then it becomes a wrong answer. Infix definitely requires. I was thinking prefix. So the only answer is postfix. So if prefix was there, it would have been an answer. If postfix is there, it is an answer that it doesn't require brackets. So that's where, how did you answer infix? 22 of you, I don't know, because infix is what you do daily. Don't you require brackets? Vaishani I see new name. Arnav Nondi, I see a new name. Good, but then I'm concerned. 26 and 16 of you answered incorrectly, which is 32 people. Half of the class answered this incorrectly. What is happening? I don't know. Operands, infix to postfix operands. We were all the while taking the operands directly to the output. Only the operators were getting pushed into the stack. Why then you stored at the bottom of the stack? Wrong answer. Ignored until operators are processed. What is that? There is no ignorance here. There is only going to be one pass. One person has gone to the output means gone. So there is no ignored until operators. That means they'll have to come back again. When the operator comes, they will have to come back again. We don't do that in infix to postfix. So this 26 and 16, I'm surprised. Really surprised. If there is a problem, let me know. We will use our spare time to make some more explanations. But 50% of the class thinking that infix to postfix operands are going somewhere, not acceptable. Still better, no change in leaderboard. Still better. Yeah, so when you are postfix evaluation, so there were three things we understood, right? One is infix to postfix. The other one was postfix evaluation. And the last one that we did was prefix to postfix. So one is infix to postfix. So our target is always postfix, okay? So infix to postfix, prefix to postfix. Prefix to postfix, we said we will do it with reverse order. And one more thing we did was postfix evaluation. All of this converted postfix evaluation. So in postfix evaluation, we will, when we pop the two operands to apply an operator, then what is happening? The operator has come in. So operator wants what? Binary operator. Two operands. So two operands will come out of the stack. Right? So that is why we will have to pop it. So that is why 66 of you answered correctly. I'm not sure. Again, 15 of you pop one operand. You can apply pop two times now to get two operands. The question was operators cause two pops, not one operand pop. Good, at least 74 of you. Srijeev has come again, and everybody has renamed themselves to capital letter. Let's see now. Okay. Dipankar, I'm seeing your name for the first time. Good. But what is happening? 20 an operator appears. Postfix evaluation. Why would an operator push something into the stack? In an operator, items are pushed into the stack when an operator appears. In a postfix evaluation, an operand appears, then only that operand will be pushed into the stack, right? So we are pushing what? We are not pushing the star, minus, plus, which is operator. We are not pushing that in postfix evaluation, right? So when an operator appears, what happens is they are popped out. The operands are popped out. That's why 20 of you got it wrong. So when an operand comes, it is directly put into the stack. I'm getting worried now on this particular topic. Some of you might get this wrong because of spelling mistake, but that is fine. We'll consider that and see. That's it. Half of the class is only answering. Shayon, Dipankar, Shreyoshi. Okay. Tanmoy has come. Priyanka, Raj, Pratyush Singh, Arjun Gupta. Good. Let's see what you have answered. Precedence. Don't know. Okay. Precedence spelling mistake, I told you. Sequence, order, hierarchy. Yeah, precedence is the correct answer. Okay, fine. Let's see the last. This is penultimate, okay. (52) leaderboard doesn't change, but then this is no parenthesis required. Of course, that is the right answer. Why did 11 of you? Number appears after operators. Numbers appear after operators. First of all, does it always have to be numbers? It cannot be alphabets. That itself strikes out this option, na? And it is read left, right to left. Why? Why will we read a postfix expression right to left? A, B plus. We will take A, then take the plus and put it inside, na? To convert a postfix into an infix. I didn't understand why we need to read right to left. So I'm surprised at this performance here, at least as far as this particular topic is concerned. Really getting worried now. Last question. Half of the class got it wrong. Dipankar, Shayan, Shreyoshi, okay. Yes. ABC plus star. Because see, bracket will be evaluated first, which becomes BC plus. And then A and BC plus will be integrated together. That is ABC plus was already there, and then the star will come to the right. So that is how it needs to be evaluated. Let us see who has come to the top. Sayon, it worked for you, is it? Capital, but Shreyoshi and Dipankar don't have capital. How come they are there? So this is the worst quiz that you have performed, guys. 55% is not something that immediately after taking a lecture I would expect, right, from that particular topic. If there was 2-3 days after this lecture, I would have accepted. Okay, chalo, next topic. And this is probably the last topic. We will spend some time here. Yeah. So what are we seeing? What are we seeing? We are seeing the right page. Okay, fine. So we are moving into linear and circular and double-ended queue, and that would complete our queue. So anybody wants to probably write on WhatsApp that queue is starting. If some of your friends were waiting for it, then let them join. Okay. Now, queue is again a data structure which can be implemented through a stack, or you can implement it through a linked list. In order to do that, when we do that, what actually comes out is a data structure which typically behaves like a queue, normal queue that you see on the roads. What happens? The queue progresses from this side, which is my front. The queue progresses from this side, and the queue the queue entry happens from behind, which is my rear. So these are the two pointers that we typically need to maintain, which is a rear pointer and a front pointer. Just like we maintain a top pointer for a stack, similarly for a queue we typically have to maintain a front pointer and a rear pointer. So entry happens from the back, exit happens from the front. So what kind of data structure is it? It is first in, first out. So that is what a queue is. Now, I told you, right, we will talk about 5 operations. So these are the 5 operations. So is full is one operation. When is a queue full? Suppose I start entering data here. What will happen? When I start entering data here, at the beginning, front and rear both are set at -1. At the beginning, front and rear both are set at -1. So when the first item enters, the first item finds a place here. The rear moves here. The front also moves here. Second item enters. The rear moves, but the front stays. So the rear moves here. Front stays. Third item enters. The rear moves. The front stays. So every time an item enters, the rear moves to the right. That is, my queue is increasing in its size. So if the queue increase in size is equal to the size -1 itself, because rear is index based and max is count, so max -1. So is full will basically return true then if rear becomes equal to max -1. That means if rear comes here, then rear will become at a position where you cannot insert any more items, right? So that is where the queue will become full. What about is empty? Is empty says that my queue is empty. When is a queue empty? I told you the condition for a queue to be empty. The queue is empty when front and rear are both -1, right? So that is what you are checking here. Actually, you can check either or and, it doesn't matter. When both of them are -1 or all of them are -1, it's all the same. It will be is empty. Now, when you have NQ, that is when you are pushing things into the stack, 3 things you have to keep in mind. Remember this, then your algorithm will be easier for you. 1, do the compliance check. What is compliance check? Compliance check is that whether you are allowed to do it, right? If you are trying to NQ something and the queue is already full, then you are not allowed. So the allowed part of it is here. This is the allowed part of it, checking whether it is full and then putting it out. Second thing is do something. I will come to this. Third thing is do the work, whatever work you are supposed to do. What was the work you are supposed to do? You are supposed to move, you are supposed to increase rear. You are supposed to increase rear to here, right? From -1, you are supposed to increase rear here. How will you do increase rear? So do a plus rear. Then rear comes here. And when rear comes here, then can you say that, okay, my queue, which was an array, at the rear position, I will put the item. So then the item comes here, right? So that is what you are doing here. So do the work means basically put the item inside that first pocket. So for that, rear has to be increased. Increase the rear, put it at the position of rear. But then this front is still at -1. So the next time you insert something, what will happen? 9 will be inserted with rear moving forward. 10 will be inserted probably the next time with rear moving forward. So in this way, rear will come here, right? Or the rear pointer will come here, and this last element, let's say, is 70. But front is still at -1. Right? So front, you cannot take out any element from -1. So when the first time some element enters, you will have to set front equal to 0, because front will have to come here so that the first element can be taken out. Otherwise, front is pointing to -1, it can never be taken out. So that's an exceptional scenario, if you ask me. Why? Because when you are entering an item, which pointer moves to the right? Which pointer moves to the right when you are entering an item? The rear moves to the right, rear moves to the right, rear moves to the right, right? So nobody takes care of front. In an NQ operation, actually speaking, nobody takes care of front. So somebody should take care of front also for the first time. That is a special case. So the special case is my third thing that I will remember. So step 1, compliance check. Step 2, special case for this NQ operation, which is not classical to this NQ operation. Normal NQ operation will move rear. It will never move front. And then do work. Do work is your actual movement of the rear. Similarly, we will have similar structure in my DQ process also. So in the DQ process, if you see, when I am trying to take out an item, then my front, it will be taken out from the front. So my rear might be here. Let us move our rear. So our rear is here, right? So our rear is at 2. This is where our rear is, and this is where our front is. So front is at 0, rear is at 2. So if I want to take out the item, compliance check is what? Can I take out an item if there are no items? So compliance check is empty, right? So that compliance check comes here. Then special case we will come later. Third case is what? Third case is do the work. So do the work means what? Do the work means that, I'm sorry, this got moved. 1 minute. Let me see if the video is proper. So the third case is what? The third case is if front, when a DQ happens, that means this item is moving out, then this space becomes empty, and what happens is, actually it doesn't become empty, it has to be freed explicitly. For our understanding, let us say that it becomes empty, and what happens is this front moves here, so the front moves to the right, so the front has to be incremented. So do work means what? Do work means store the value that is in front and increment front. Store the value that is in front, increment front, because when you increment front you have lost that value. So store the value somewhere, because you have to return that value, because you are asked to DQ means return the first value. So now let's talk about what is the special thing. Special thing is, by doing this over and over and over again, what will happen? Front will keep on moving forward. So front will go here, from here to here, from here to here, from here to here, right? And when at here, then front is here and let's say I had some more elements here, 12 and 13 also, so my rear was also here, so my rear was also here. So front keeps on moving this way, this way, this way, and finally when front is here and the final DQ happens, then this element is also not there. So front and rear are both equal now. Front and rear are both equal, because front has come all the way from here, all the way from here, and become equal by removing all elements one at a time. So this element is also removed by the time it reaches there. So then what happens? Front becomes equal to rear. If front becomes equal to rear, it is a condition of an empty queue. The queue is no more. So empty queue is defined as what? Front and rear minus 1. We had discussed that initially, that we'll set front and rear will be minus 1. That is my special case. So when you are handling NQ and DQ operations, please remember these three things: compliance check, special case, do work. I think that way you can remember things. What is happening? Problem is that this front moving forward means that it is going here, and suddenly let's take an example. Okay, let's take an example. Okay, now let me increase the thickness. Yeah, so if I take my front outside, let me put some elements: 20, 30, 15, 7. Right now I am taking out this DQ, so front, which was here, moves here. I am taking out this 30, front moves here. By the way, my rear was here. Next time when I am doing this, front movement, that is taking out 15, front moves here. Now front, when it has moved there, then what is happening is that it says that my rear, or whenever I want to actually enter an item, actually I made a mistake here. My Q also had 10 here, and this R was not here, this R was here, right? So my R was here and my front came to this point. Now if you want somebody to enter, then R has to move to the right. If you see NQ operation, R is plus plus, that means R has to move to the right. R cannot move to the right, so unnecessarily the Q will be reported as full, which means in spite of not having any elements here, you are being reported as Q is full, because the spaces are not getting utilized. Why? Because front is keeping on moving forward. Finally it is here. So these spaces, which pointer will handle? No pointer is here to handle these spaces, so they are empty. And that is the wastage of a memory. And limited number of insertions means you cannot insert, you can only insert 5 things or 2 things or 3 things. Cannot go on inserting, deleting in a linear queue. So that is why it is called limited number of insertions. Now comes the problem solver, which is circular queue. Circular queue says that take a linear queue and join their ends. So this was my starting end of the linear queue and this was my ending end of the linear queue. So join both the ends, right? In that case you get a circle. So in this circular queue I have kept on the left the linear queue syntax or the algo, and this is my circular queue. So just the delta portion I have marked. So if you understand how to write linear queue, you can very well understand how to write circular queue by just remembering these three things. That's all you need to remember. Rest everything remains the same. First thing, when you enqueue, what is happening? In a linear queue, what was happening in an enqueue process? R started to move like this. So R was getting plus plus. So R here also might move from here to here. R plus plus, R plus plus, R plus plus, R plus plus. And then where will R go? Now in a circular queue, we need to allow R to move here. Then only the reusing the blank spaces will be effectively utilized. So if we do that, then 4 has to go to 0. So how will 4 go to 0? You take the advantage of swinging the number line. So you will swing the number line by saying that I will increment my rear. But at the same time, if I get something which is beyond my upper bound, I will switch back to the correct position. And that can only be possible if you do a modulo of max. So if I get 4 and I increment by 1, then I get 5, which is crossing my index upper bound. Index upper bound is only 4. So 5 needs to be converted to 0. And that can only be possible if I do a modulo of this 5 with the max. Now will it work here in the normal situation? If R is here, will this plus 1 modulo max work? Let us see. If R is at 0, plus 1 means 1. So 1 modulo 5 is 1. So it goes to 1. So it is working in the normal scenario. Now, you can always say, I want to do a if else here. You can do an if else. Nobody will stop you. But this is more effective way of writing the code. Now, the next operation that we know about is the DQ operation. DQ operation is taking things out from the queue. So if we have to take things out from the queue, then what we will do is we will take this queue and let's say when we do DQ, what happens? Front moves front. DQ means front will move front. So you had somebody here. So this item, if you have to pull out, what will happen? Front will move here. That is how we DQ, right? So front here means this item is lost, right? So that is why we say that this space is also lost. So front moves front. So if front moves like this and comes to the end, it has to come back here and start using the vacant space. So front moves from here to here to here to here and to here, and then front comes here. So front, next time it increases, it has to go here. Again the same thing. We will have to do a when we do a DQ, we'll have to do a front plus 1 modulo max. So front will be incremented, and in case it crosses the boundary, we will do a modulo max to bring it back into the boundary. And that is the same thing that we will do for isFull also. isFull is when let's check isFull. Okay, isFull is going to happen in 2 conditions. One, this particular queue is full if my rear is here, my front is here. Why? Because front here means this has some element, and rear here means rear has come all the way like this and come here. That means these definitely would have some elements, 23, 55, 69, 79, right? So they definitely have some elements. So if rear plus 1 rear plus 1 is equal to front, then we have a full condition. So instead of saying that, can I say rear plus 1 modulo max? So if my rear is at 4, then 4 plus 1 is 5. 5 modulo max is 0, and 0 is equal to my front. So my rear plus 1 modulo max becomes equal to my front, and hence I can say that my Q is full. In another case, we can actually see that why this is also okay when rear and front are in a safe zone. When I say safe zone, there is no crossing the boundaries. So if my rear is here, my front is here, then it is quite evident that rear would have moved all the way from here and come here, right? So that means that this is there is an element here, there is an element here, element here, element here. Now rear plus 1 means what? 1 plus 1. 1 plus 1 is 2, which is equal to front. So it is full. But then we have given a general formula. That means this should also work. So let us see. 1 plus 1 modulo 5 is what? 2 modulo 5. So 2 modulo 5 is 2. So this also works here. So that is how we will need to interpret circular Q, right? That this is the 2 or 3 changes that you just need to make on a linear Q. Just make sure that you understand when is the full condition happening, and how are we actually making sure that we are rolling or swinging to the other side of the number line using the modulo operator. So that is on the circular Q. And this is the applications of questions on that. Circular Q is implemented using an array of size 10. The array index starts with 0, right? So there is a circular Q like this, and there are 10 pockets is what they are saying. Array of size 10. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I have drawn much more. Okay, so this is how it should have been. So this is my size 10 circular Q, and the array index starts with 0. Okay, front is at 6, so front is here, right? And rear is at 9, rear is here. So rear has definitely moved from here to here, right, all the way there. The insertion of the next element, rear has to move front plus plus, right? Rear has to move plus plus. So 9 has to go to 0. 9 can go to 0 only with this logic, rear plus 1 modulo size, right? So we have learnt about it. So they want the insertion of the next element will take place at what array index? It will take place at 0 array index. Rear plus 1 modulo size. Rear is 9 plus 1 is 10. Modulo size is 10. So which is 0, and that is where the next insertion will take place, which is correct. Right? So when front is here and rear is here, this entire space is wasted, na? So we have to use this space. So rear will keep on moving till it covers that. Right? So that is why circular Q is important from a execution standpoint. So from a stack versus queue, I think you know about this already. LIFO, FIFO, stack insertion and deletion, where they are performed, that anyway you are clear. And where is stack and queue used? So stack typically is used in your undo redo operations, right? So when you keep on typing something or doing some actions, the last action will be at the top. So you can undo the last action. So that means that you can actually use a stack for that. And for a queue, it is more of a round robin scheduler where CPU scheduling or printer queues or buff, any kind of queue in your operating system that is used can be used using a queue. So that's on the application side. Why circular queue is better than simple queue? We know about it. We can reuse the free space. We can do continuous NQ DQ, right? We saw that as a limitation, and no shifting needed after deletion. Now, no shifting needed after deletion means what? If you see a queue like this, and if you see that this is a normal linear queue.
1 minute, let me see what is there left.
Okay, so if you see a queue out like this, in this queue, if I have some element here, let's say 23, 34, I have some element like this, or let's make this queue a bit fatter. Let's make it 45, 69, 5, 70, 89, right? A full queue. Now this is dequeued. Then front moves here, rear is here, right? Then does this happen in reality? When somebody moves out, right, does the counter that we are standing, so queue means that we are standing in front of a counter. What is happening here? The person has moved out, the other person is standing wherever he is standing. Second person is standing wherever he is standing. So has the counter come to him? So he should move front, na? That is what happens. If he should move front, the other person should also move front. This is how it should have happened in a queue. And that is what this says. No shifting needed after deletion. So when we are deleting this element, ideally speaking, all these elements should have been shifted one step to the left. That is how a queue should work in a physical reality. We are not doing it because we will consume order of n. That is why we are not doing it. But it is allowed, or it is automatically possible in a circular queue. So that is the reasoning that I explained. Suppose a queue is implemented, write an algorithm to insert a new element at the kth position of the array. So the kth position of the array, if we have to insert, let's take an array like this. A queue is implemented using an array. Right, so if this is an array 0, 1, 2, 3, 4, 5, 6 and the array is not full, right? So the array is still there in terms of being empty. So we have, let's say, these elements inside the array: 7, 29, 35, 6, 5, 80. I want to insert an element here. Right, so I want to insert an element at a particular position. So that is what I will say, that if I have to insert a particular position, then first of all I need to know my queue's front, I need to know my queue's rear. Right, so those are the two things I definitely need to know. I need to know that name of my queue. My name of my queue is, let's say, queue. Right, that is the name of the array. Then what we will do is at the position k, so the position or index, whatever you choose, ultimately you have to reach here. So at the position k, we will come from this side. So we will run a loop from the right and we will reach this position. So when we run a loop from the right and reach this position, then can we say that queue of I plus 1, wherever we have reached, is I, let's say this is my I. Queue of I plus 1 is equal to Q of I. What happens is, we have reached this position I because somebody told us to insert it at that position. So from the left we came and we reached that position. That means we are now pointing to that position. So when we point to that position, can we say this 6 no longer is here, it comes here. Right, so this 6 no longer is here, it comes here. And similarly, we will say that what we are doing is, this is getting lost. So what we are doing is, from the right, and let me just delete this. This is the last step that is happening. So I came to the last step directly. So suppose this is where we have to insert. Now my I starts from here. Let us say my I starts from here. So what I will say is this. So this means what? Q I plus 1 is this. So at this position I am putting this. And this is gone. Right, at this position I am putting this. This is still there, but it will get overwritten. Next time I move I here. Then this now gets put here. So this becomes overwritten by 5. Next time I move it here. So this becomes overwritten by 6. Right, and I am at this particular position. So now I can insert whatever element I wanted to insert. Let's say that was 39. So I can insert this 39 here. My 6 is already preserved, my 5 is already preserved, my 80 is already preserved. So all the items I took and I moved one item at a time to the right, created a space, moved the next item at a time, created a space, moved the next item at a time, created a space. Finally, we got the space for us to insert. So that is why we say that for I that is in the rear down to k means the position where we want to insert, we will do this iteration so that we get the freed position, and then we will insert our item there. So once we insert our item, what should happen? This rear which was here should go here, and that's why we say rear equal to rear plus 1. So that is the algo for your insert on the circular queue. Now definitions of queue and its applications, I hope I don't need to do this with you again. Next, queue questions on following data structures can be implemented to use queue. Of course, we can use both stack and linked list to implement a queue. There is no stopping us, we can use both. Right algorithm for push and pop, we have already done it. Right algorithm to delete an element, we have done it. Delete, time complexity. Circular queue, if you have to delete an item, it is an order of 1. There is no loop that you are doing to delete an item, so the time complexity will always be an order of 1. What else is there? Yeah, so DQ, we are at 5 o'clock. So I'm going to give a break now before we start DQ. Let us take a 15 minutes break if all of you are okay, and we will finish this off in half an hour. So by 6 o'clock we'll close the class. So we'll come back at 5:15. Yes, catch up night. I also need the break. My throat is gone. Yes, array and linked list, unless I mention something else. Priyanshu, I don't think 15 minutes I'll get tea, but let's see if I can get some tea. Don't go anywhere, be here. After 15 minutes we are starting. No, we are not ending, Vishal. We are starting after 15 minutes. Whoever is back, please join. Linear and circular QQs. I'm waiting for others to join because I see 78. Before the break we were 100. Not sure how long it takes, or probably they broke off for the day, which is okay. I'll just wait for 1 more minute and then we'll get started. Okay, let's start off. 76 of you are here. Let's see. %, okay, not bad. Rohit, I am seeing a new name here. Good, Rohit. Catch up. Let's see next. All of you should get this correct. How 50, 60, 18 of you said rare. 57 said front. From a queue, think about it, in the line, do you remove people from the back that you are saying rare? Then why here it will be rare? Common sense, na? Chalo, next. Good. Thank you. At least 86% of you have answered this correctly. I see the same names now. Space gets wasted in a linear queue, hence we require a circular queue. That is what we have established. What happened? Front. Front might have moved somewhere. How do you know front? Front need not always be at 0, na? After it reaches the end, it will move to the front. So the end is for a queue of size, let's say 5, the end is at 4. So when the rear reaches the last index means it has reached 4. Next, what will happen? It will move to 0. Why front? Front may have moved to 3, 4, whatever, or 2. Who knows? Front may have moved. So why 27 of you got confused with front? I don't know. Circular queue means that is the condition. Na? Rear has to move to 0. That is why that modulo is there. Come on. Chalo, next. Now don't get this wrong, come on. "86, still some of you have answered it wrongly. 8 says recursion. Okay. You didn't notice the modulo. Otherwise you would have answered otherwise. Next. Queue full. Okay, Deyanshu Raj, Shayan Das, Asifur, okay, same names. Rear equal to front. Yes, rear equal to front, but we are talking about a circular view, friends. So rear equal to front cannot be. So rear equal to front is a problem here. Right? So rear equal to front is okay when you talk about linear queue, but not for a circular queue. So wherever you see modulo in a circular queue, typically that would be the answer, if that is how you may want to remember it. Let's see how many of you get this correct. If you have the logic, you will understand what word it is. I've given some more time. Okay, no change in leaderboard, 68%. Okay, not bad considering the question. Forward, behind, no. Linear queue, forward hi jabe na. Linear queue, the front will always move forward. Behind, only it will go in DQ, which we have not discussed yet. We will discuss that. Okay. Next. You need to understand the meaning of the word follows. Then you will get this correct. Good. Good. 80% on a typable answer. I am impressed. Good. 0 is the answer. Because follows means after, right? So after the size, it is always 0. Next question. All of you should get this correct now. Still some 2 or 3 of you got it incorrect. Vishal has come up good. 8 of you full. You just got confused. Front and rear -1 is an empty queue. I just now explained. Okay, good. This quiz was much better than the last quiz. Thank you for that. Let's see who are the winners. Shreyoshi, Deanshu, Shayan. Okay, Shayan, your trick worked probably, but that's okay. Let's see if you ace the others. See, 71% is where we are landing, which is good. So let us quickly finish off with our DQ, and then we can get finished with the last quiz of the day, and then we can break off. Okay, so this gone, this start. Yes. So what is a DQ? Don't confuse DQ operation with DQ queue. So there is one operation called DQ, right? So this is deletion operation, right? So that is what we do in a queue, but here we are calling it double-ended queue. So that is why this is called as DQ, double-ended queue, right? So DQ is why it is double-ended, because if you see this queue here, then in this queue here, we know that in a queue, what happens? The deletion happens from here and the insertion happens from here. So the deletion will always happen from the front and insertion will always happen from the rear. That we know, right? So the double-ended queue allows the insertion also to happen from the front, and ulta deletion to be happening from the rear. So net if wherever in a normal queue, wherever you are actually doing the normal operations, there put the next operation also. So if you are doing a normal operation in the front of the queue, then that normal operation was deletion, because in the front of the queue you do DQ, which is deletion, and in the back of the queue you do NQ, which is insertion. So if you do deletion here, then do an insertion here, which is the ulta of deletion. And if you would have done insertion here, do also a deletion here, which is again the ulta of deletion. So net insertion and deletion in both ends of the queue, right? So that is a double-ended queue. Now this double-ended queue, if I say that I will not allow the insertion to happen from here and the deletion to happen from here, I will not allow this to happen. Instead, I will definitely allow the insertion to happen from here and deletion to happen from here. This I will allow. Then the queue that actually becomes is a stack. Right? I hope you can understand. We have blocked this complete end, and only this end we can insert, this end only we can take out. So this is a stack then. Right? And similarly, if it is supposed to behave as a normal queue, then what do? We will allow the addition from one end and the removal from another. This is our front and this is our rear. So then this entire thing becomes a queue. So what are we not allowing? We are not allowing removal from here. This is not allowed. We are not allowing insertion from here. This is not allowed. So if we not allow certain combinations of these four operations, we either get a stack or we either get a queue. So that is important for you to understand, therefore, that a DQ behaves as a stack sometimes and behaves as a queue sometimes. Now what is an input restricted queue? Input restricted queue is where you have restricted insertion at one of the ends. So instead of if we have a queue like this, then we will say that input restricted queue is insertion will be only here, but deletion can happen anywhere. So deletion can happen from here, deletion can happen from here. This is an input restricted queue. Insertion can happen only at one end, usually the rear, and that is why I have put it at the rear. Right? In a output restricted queue, just the ulta. So the output will happen only at one end, and at the other end both insertion is possible at both the ends. So insertion is possible at both the ends means insertion will happen here, insertion will happen here, but output will be only once. Right? So that is where the output restricted queue lies. So these are the two types of queues. Please remember these two types of DQs rather, and how the DQ can be converted to a stack, how the DQ can be converted to a queue. These are two questions that typically come. Now if I come to the operations, I will try to sanitize the operations now. When I say sanitize, you don't need to remember all operations. See, when we have a DQ like this, then I have to take care of one operation here, one operation here, one operation here, one operation here. These are my four operations that I have to take care. Insert at the front, insert at the rear, delete at the front, delete at the rear. We are talking about insert now. So there will be insert at front and insert at rear. Now in a normal queue, what kind of insert do? You do an insert at rear. So in a normal queue, you will do an NQ, because in normal queue there was no rear front concept. We called it one word. Here we cannot call it one word. Insert cannot be called NQ now anymore, because insert has to be qualified with whether it is rear or whether it is front. Right? So that's why we will have to qualify it as rear, because when we say NQ, what are we doing in a circular queue? In a circular queue, when we were saying NQ, or for that matter any queue, when we say NQ, right, what is happening? The happening part of it is that the entry of the new element will always happen from rear. That means it is no different from insert rear. So NQ is nothing but insert rear. So then the code should be exactly the same, and the code is exactly the same. You don't need to write the code. So if you know the circular queue code, then just think on these lines that what is common between circular queue and DQ. Circular queue and DQ, the common part is insertion happens from the rear. So the code of insertion happens from the rear is the same. Right? So that way I don't need to work on this code. So I just need to focus on insert front. So insert front means what? Insert front means that I am going to insert an element which will bring my front back, which means that if you see front, let's say moved here, and rear is, let's say, here. So front has moved here. So if I say insert front, which was never possible, remember, insert was always from the rear. Now insert front is never possible, but except for DQ. So if I say insert front, that means somebody will come, wants to come here. Right? I hope you are understanding. Front is here, insert front. Normal process, front will move forward, na? Whenever somebody exits, front moves forward. That is what we know. Whenever a DQ happens, front moves forward. We're not talking DQ. We are not talking ulta, insert. So if insert happens, then ulta will happen. It will not move forward. It will move backward. So the front will need to move backward in order to accommodate that insert. Right? Because it cannot move this side, because this side is full, na? So it will move backward. So if it has to move backward, then this is what we have to actually take care of. Why? Because normal backward is okay. Front equal to front minus 1. That is okay. But then while doing it, if front was here, it is okay. If front was here, then if we had to move it backward, then suppose rear was not here. Suppose rear was here. Then front is here. So front is at 0. So front has to move here. How will front minus 1 take care of it? So 0 minus 1 is minus 1. And we have to make it 4. So what we do is we take minus 1 and add the size of the queue with it. Immediately we get 4. 4 modulo front minus 1 plus size, which is our what is this? Front minus 1. Front was 0. 0 minus 1 is minus 1. Minus 1 plus 5 is plus 4. Plus 4 modulo 5 is 4. So we get 4 as our target index. So this takes us from this F front becoming 0 to moving backwards, that is taking it to 4. Now normal process should also work. This is the special case, right? That when we were actually moving across the index boundary. So let us check the normal process also. So the normal process says front is here, front wants to move backward. Will it work? So front is at 0, sorry, front is at 1. Front wants to move backward with this syntax. It should become 0. So front minus 1, front is at 1, minus 1 is equal to 0, and that plus size is equal to 5. So 5 modulo 5 is equal to 0. So front definitely moves to 0 with this syntax also. And that's all. The rest of the syntax is exactly the same as your insert rear. Right? So that's the insert front. So insert front, all you need to do is normal inserts will move the front to the right, and insert front will move the front to the left. That's all. That's the only difference. Next, DQ for delete. We talked about insert. Now delete also the same thing. So similarly, if you imagine a queue and you imagine deletion, deletion happens from the front. So if deletion happens from the front, then imagine this. When deletion is happening from this side, right? So this is my front and this is my rear. Somehow I'm thinking that in the last slide I might have taken front and rear interchangeably. If I have, and if you have understood, it is okay, and if I have not, then it's also okay. But then if you think that I made a mistake, please point me out. Now when I say front, delete front, then this front is supposed to be deleted. That is, this element is supposed to be deleted. What happens to front? Front will move forward, right? So do you think this is something that you saw in a circular queue? Yes, DQ is the operation you saw in the circular queue, where from the front we were deleting an item. Circular queue, linear queue, whatever it is, DQ was an operation. DQ means what? In a queue, somebody is supposed to come out when he is first, right? So from the front only he will come out, na? So then DQ is nothing but delete front, right? So circular queue, whatever function we had as DQ, in a DQ we have it as delete front, and this is the same. We don't need to worry about it. This is the same function that is there. So if we have written it once in circular queue, we can replicate in a DQ. On the circular queue for the delete rare, this is something we never do. We don't delete an item from this side, and that is what we need to write separately. So if you want to delete, how does rare move? Think about how rare moves. Doesn't rare move like this? Rare moves like this. So if you delete something, then rare should move like this, right? So rare should be decreased. So that's what we need to do. Rare should be decreased. If rare is here, it should be decreased to here. If rare is here, it should be decreased to here. Suppose if rare is here, how will it be decreased to here? Same logic. We will say rare minus 1 plus size. So 0 minus 1, which is minus 1, plus size, which is 5, which gives me 4. 4 modulo 5 will give me 4. So 4 will be my target position of the rare. And that's all you need to keep in mind. So if you understand what you are doing, the entire rest of the code remains the same. All you are changing is here, where you are saying that delete from rare does the ulta of what the rare pointer moves. Rare pointer moves from left to right. Delete from where will move it from right to left. That means it will decrease, and hence it will move to the left. And when it moves to the left, it will reach a state when it will cross 0. And that is where you have to take care. So that is what is being done here, delete rare. Peak, same thing, nothing much to say here. Peak and Q check. Q check is your is empty and is full. If you remember, I talked about these 5 operations at the beginning, right? So peak, what is peak? From where you are deleting, you will peak that without deleting. So if this is a standard operation, right? This is a standard operation of a queue. Deleting from the front is a standard operation. So the peak front, the normal peak operation that we had is nothing but get front or peak front, which is the same. No need to do it, right? And the peak rare, because now you can delete from the rare also. So you also need to have a peak rare. Peak rare will be the same as, peak rare will be a new function that we need to incorporate. And that peak rare will be very, very similar to our this function, which is delete, where we, instead of moving the pointer, right? We are moving the pointer here. We will not move the pointer. That's all. So you will just return the value, not moving the pointer. That's what peak is. Peak is just delete without moving the pointer. So I didn't put that here. I'm sure you can understand that. And is empty, which is empty, will remain the same when we say is empty, because in is empty case, we had checked front and rear minus 1. So front and rear as minus 1 at the beginning is what is empty is for a normal queue, for this queue also. So is empty remains the same, but is full will change, right? Is full will actually change to accommodate the fact that we will not only need to check that front, if front is 0 and rear is equal to size minus 1, then this is a full queue because this has gone the entire circle. So front is at 0 and front and rear is at size minus 1. So if this is the case, then we have a is full, or we can have front equal to rear plus 1 modulo size. This we have already done. So front equal to rear plus 1 modulo size is like this. I will show you that combination also. So when is that happening? If we have front here and if we have rear here and front here, right, then what is happening is this rear, if we increase by 1, if we increase 0 plus 1, right, then do a modulo of 5, then we will get 1, and this 1 is equal to my front, and hence this particular queue is full, because if front is here, rear is here, everything is filled up from here to here. right? So these are the two cases. This is the same case that we saw in a circular queue. So nothing different. Is empty. That's why I said is empty is exactly the same, and that's why it looks exactly the same. Only in is full, we will have to check that additional thing. In fact, this part of is full is also the same, which we just now discussed, right? So that's where only this part that you saw here, which is front equal to 0 and rear equal to size minus 1, is the new thing that we have we have to introduce when we are talking is full. The rest of the code is exactly the same as a circular queue. So be a bit intelligent, try to find out the deltas. I've made an attempt. You see this and try to find out the deltas between DQ and circular queue. Don't do a ocean burning and ocean boiling and try to figure out the entire code base. Always try to figure out the delta. Take one code base and incrementally figure out the delta. So what are the types of queues? Now that we know DQ is also a type of a queue, we have a simple queue. Explain each. So you'll have to explain. So I think you can explain what is a queue means. You will talk about the FIFO, LIFO, etc. of it. Then you will talk about what are its advantages and what are its disadvantages. That is basically what it is used for and what it cannot be used for. So those are the things that are already mentioned here. Feel free to read it. You know most of it, and that's something that you can actually, I'm sure you can generate. Priority queue I have not touched upon. It comes very rarely, but priority queue is where the DQ and NQ will not happen basis where it is located. It will happen basis its priority. So if the priority of an item, so let's say I want to insert 7, 9, 10, let's say 11. Priority of this is 2, priority of this is 4, priority of this is 3, and priority of this is 1. Then this 10 will be inserted first, right? And then we will insert 11, which is priority 2. Then we will insert 9, and then we will insert 7. So that is how you create a priority queue. Now when you actually DQ, you will get 10, which is your priority 1, and hence you are satisfying the priority. That is a priority queue. That's all that is a priority queue. So just read through this. I'm sure you can. This is a theoretical question. It will give you some 6-7 marks if you can answer this question. A linear list in which elements can be added or removed at either end but not in the middle. Can you answer? Just type in the chat. Linear list in which elements can be added or removed at either end but not in the middle. Let's see the chat. Double-ended queue. Okay. Nice, good, good. Both sides we can insert and delete means double-ended queue, but we cannot do it in the middle. What is a DQ is the next question. Okay. So if the stream is coming, it's fine. Let's move on. So the question was, a DQ can be used as a stack. What is a DQ? I'm sure you can answer. But DQ can be used as a stack and as a queue, or both as a stack as a queue, right? So that is something that all of you are aware of by now. We have discussed that we can use a DQ both as a stack and a queue, and hence the answer is this, right? So that is on this particular question. Next question is on, in fact there is no next question. We are done for the day, and we are done for the last quiz now. So we will do the last quiz and wrap up. So let's go to the quiz. Let's see if you can give me a 70% marks in this DQ quiz. Okay, I'm sharing the QR. Chalo, join quickly. We will start at 75. Seven more, come on. Three more. Okay, let's start. Shayan Gitika Prakash, 51%. Front deletion only, rear deletion, okay, 13 only, rear insertion, that is surprising. Output restricted. Output restricted means output will be only from one direction. That means output means what? Deletion. So deletion will be only from one direction. Deletion will not happen from both the directions. That is what is output restricted. So I don't understand why rear insertion is an output restricted. Rear insertion is rear insertion. I mean, you can insert it, but it is not going to make it an output restricted queue. Next question. All of you should get this correct, no? Good. Good, and thank you. 91%. Next question. Okay, this is also good. 79, nice. Next question. Okay, kind of. DQ can simulate a queue. What is a queue? A queue is deletion from beginning and insertion from behind. Right? So insertion at rear and deletion from beginning. That is the answer. Just think logically. 15 of you who have answered. DQ can simulate a queue. That is, it can behave like a queue. Delete at both ends doesn't happen in a queue. It happens in a DQ. Right, so the next question. A DQ can behave as a stack by performing both insertion and deletion at the stack. What happens? Where does deletion happen? There are only 4 letters. What matches? Shayon Arno Pragati. Good, Pragati, I am seeing you in the leader list. Good. Yeah. So it will happen at the rear. You cannot create in the same, right? Same means what? It could front or rear, right? It has to happen as a stack. So it cannot be same. You have to mention rear. So that's our assignment. And I'm closing that. Pragati, Arnab, Shayan. Okay. So Shayan, back to back 3 after you changed your name. Huh? Good. Okay. So that's all, guys, for today. And we will meet tomorrow. Tomorrow, most important 2 topics. Trees and our, what was the other topic I forgot? Linked list. Right. Most important 2 topics, and these 2 topics come. A lot of questions will come. The weightage on these 2 topics are much more than what we discussed today. So don't miss it by any chance. I hope you had fun, and any feedback, please let me know over my WhatsApp or over any of the chats. I will keep reading it. So let me know if anything that we have discussed is wrong. I will publish a Google Sheet, and you can actually have that Google Sheet filled up in terms of the questions that you have, which we will discuss in our free time. Okay, chalo. Thank you. Bye-bye.